So now we are also live on YouTube. Hi, Deepak.
Hey, Deepak. Hey, Ankit.
Hi, Deepak. We are already live and recording. Hi, folks. I think we'll wait a couple of minutes more. I can see the participant list growing by the second. So let's give folks a few minutes to join in, and then we can get started. Hi, folks. I still see lots of people are joining in minute by minute. So let's wait a minute or two more, and then we can get started. All right, I think we are going to get started here. So anything longer than this, 2.5 minutes or so, that will damage Swiss Time's credibility. So it's my great pleasure to welcome you all on behalf of my co-organizer Debopam Bhattacharjee and myself. My name is Ankit Singla. I'm a professor of computer networking, and I run the network design lab in the computer science department at ETH Zurich. LEOCONN has a very diverse audience, and I think I need to provide enough context to keep everyone on board. So my talk will address these 3 questions. What's this all about? Who cares? Who's involved? And what are the open challenges and opportunities in this area? So what is this all about? We'll discuss 2 big use cases for low Earth orbit networking. On the left here, using large constellations of satellites to provide internet service. And on the right, using smaller satellite fleets for imaging applications. We'll start with imaging because Day 1's program primarily centers on this. Satellite imagery has numerous applications like monitoring natural phenomena such as volcanoes, forest fires, floods, keeping an eye on agriculture, land use, vegetation changes like in rainforests, understanding glaciers, evolution of ice sheets, and other phenomena that help us understand the planet's health, and many more such applications. Across all these applications, at a very high level, this is what's happening. A satellite or a set of satellites is taking pictures. Pictures is overloaded here. It can be any type of sensing instrument on a satellite that's producing sensor data. This data is then transmitted to ground stations, like this one here, over radio links, which then transmit the data to a cluster or data center facility where it can be processed, used in applications, stored, archived, etc. This here is a coarse summary snapshot of today's LEO imaging ecosystem. We have hundreds of satellites in orbit doing various imaging tasks. These satellites together produce tens to hundreds of terabytes per day of data. This huge data volume creates bottlenecks for both data download, getting that data down to Earth from the satellites, and data compute, processing of that data to produce actionable insights or information. These bottlenecks are at the heart of the networks and systems challenges that we are interested in. And these challenges are getting more and more urgent over time. I'll explain this urgency with a schematic here. On the x-axis here is the frequency with which we image a particular part of the planet. And on the y-axis is at what resolution we are doing this. How small are the smallest objects that we can distinguish in the imaging that we do. For a fixed cost system, there's a Pareto frontier, a trade-off between these 2 factors, and you can't do better than that, right? So either you can have high resolution imaging and do it infrequently, or do much more frequent imaging, but at much lower resolution. And there's various trade-off points along the curve. Now, the key thing is that this curve is shifting upward and rightward over time as the cost of satellite launches improves, decreases, the technology for imaging improves, the satellites get more miniaturized, etc. So there's a reduction in cost, and at the same time, there's increasing value and willingness to invest more money into this ecosystem of imaging as the market expands with more and more applications, partly enabled by convenient cloud processing. So these systems, satellite fleets, are evolving towards greater and greater scale. And as you can imagine on this right corner, as you keep moving towards rightwards and upwards with high resolution images taken more and more frequently, we get a huge data deluge and subsequently a processing or compute demand that's increasing very rapidly. And this is what's sharpening these systems and networking challenges involved. I'll discuss some of these challenges later, but let's first look briefly at what's happening on the broadband side as well. Here, the goal is to use hundreds or thousands of LEO satellites to provide internet connectivity. Such global coverage is meant to address the gaps in connectivity serving underserved populations, but also other challenging connectivity scenarios like on the seas and in flight. So how does this work? Each LEO satellite provides service in a coverage zone underneath itself, as shown here. Terminals in this zone can communicate with the satellite using radio frequency beams. A particular ground terminal can be seen from a particular satellite only for a few minutes, and thus requires frequent handoffs to successive satellites as they move around to maintain continuous coverage. A terminal S can send data to a destination P in several ways, one of which is to send it up to a satellite through a radio link. And then if the satellite constellation supports inter-satellite connectivity using lasers, for example, then you'll perhaps take several satellite-to-satellite hops and then downlink the data again to the destination using a radio link. Another way of doing this, if the satellite constellation does not have inter-satellite links, is to bounce the data back and forth between the terrestrial sphere and the satellites, as shown here. This is called bent pipe connectivity. Of course, there are many flavors of this. Another iteration would involve just getting the data from a source sender to a ground station, and then networking the ground station to the internet through terrestrial fiber, and using that terrestrial fiber connectivity to reach the destination. So these are several ways in which LEO connectivity can be implemented. Before the ongoing LEO networking revolution, prior satellite-based consumer broadband operated primarily in geostationary orbit, as shown here. With a handful of geostationary satellites, one can cover a large part of the planet, as this graphic shows, with this coverage cone. But this results in extremely large latencies or round-trip times, RTTs, because of the long distances involved. Geostationary satellites necessarily have to orbit at this altitude of about 36,000 kilometers. Operating in low Earth orbit allows much shorter RTTs, and latencies can be comparable to terrestrial fiber networks. In fact, across long distance communication, these networks, LEO networks, can be faster than fiber routes. One flip side, however, is that the coverage cone of a satellite is now much smaller just because of the visibility a satellite has. And we need many more to cover the globe. We'll use a schematic again to look at the design space here. On the x-axis is some notion of coverage, network capacity, market size. It's deliberately loose. And on the y-axis is latency that the network provides. There are at least two incumbent providers that use a handful of GEO satellites to serve about 1 million customers, providing latencies of about a few hundred milliseconds. There's also at least one incumbent provider in the LEO networking space with tens of satellites, which in theory could provide a few tens of milliseconds of end-to-end latencies, but it serves primarily niches like satellite telephony. The new constellations are on track to occupy this spot on this plot. That is massive scale in low Earth orbit. Such networks can serve tens of millions of customers. SpaceX has already filed requests for serving about 5 million customers in the US. And they've already demonstrated measurements with 20 to 30 milliseconds of latency round trip. And this is with partial deployments of their constellation. So this is roughly the space where the new massive scale LEO constellations are on target to operate. We could move further rightwards here. This will largely depend on how much market demand there is for such connectivity. This is not clear yet. Regardless, these networks, even at this minimal scale that I think we'll hit very soon, are high value, complex, and dynamic. Many of the network and system challenges that we saw in the LEO imaging space are even exacerbated here because of the scale of these networks. So this bottom line connects these two themes today, and that's why we are addressing them both together at LEOCONN. So now let's move on to the second question. Who cares? Who is involved in this space? So I hope that I've given you a sense of the interesting applications involved and why they are of value. But I also want to touch on recent industry developments. There's quite a lot of hectic activity in both spaces. On the imaging side, Azure and AWS recently launched ground station as a service platforms of their own. Google and Planet Labs are partnering on imaging applications. Microsoft and KSAT, which is a ground station network, are partnering on imaging ground stations. On the broadband side, Microsoft and Google are partnering with Starlink to provide connectivity for their data centers. Microsoft also has such partnerships with SES and Viasat. The SES partnership touches both the imaging space and data center connectivity. Another player in the space, Mynaric, which does space laser tech, has a cooperation with a large constellation operator for inter-satellite link connectivity. And these are just the biggest names. These folks, some of them are also presenting at LEOCONN, and we are looking forward to great talks from all of them on both sides. Among our attendees alone, however, we can see that there's a huge ecosystem involved. Across the several hundred registered attendees and several people watching on live YouTube streams, we have at least 35 space sector companies, including companies involved in imaging, ground station networks, broadband constellations as well. We also have, apart from these new space players, traditional companies that do networking, like networking vendors providing equipment or software for managing and running networks, cloud companies, telcos, several countries' government agencies, as well as a large number of academics. We have attendees registered from 29 of the top 30 global universities, and 17 of these folks are professors at these universities. Now, keep in mind that this is not 10 attendees from network vendors. This is 10 unique network vendors. Given that there's not that many large network vendors, we have pretty good coverage even in these terrestrial spaces of activity. So there's a lot of interest in this LEO networking space right now. So now let's look at some open challenges and opportunities ahead of us. I'll use this picture as a grounding graphic and refer to research threads of relevance for each of these players, starting with imaging satellites. The challenge here stems from the large data volumes involved, on which I hinted earlier. The satellite to ground station links are extremely limited in bandwidth, and on each pass, a satellite can see a particular ground station for only a few minutes. Further, the uplinks are even more severely constrained. So the path for sending data to a satellite is even more severely constrained, often by as much as 1,000 times. Further, multiple ground stations and satellites create interesting challenges in scheduling. This can be of many flavors. Some of it is well studied in the satellite network systems conferences. However, most of the content there focuses on satellite design or the low-layer hardware design for the wireless channel, not the types of computer systems and computer networking problems that we'll focus on, especially at the higher layers. So there's a lot of opportunity for doing new work here because several of these past methods are no longer keeping up with the scale of these new imaging fleets. Another such research direction that's going to be interesting is potentially applying techniques from video streaming analytics. There's a rich body of work in networking conferences like SIGCOMM and NSDI, with some of this work proposing, for instance, using the receiver side, so in this case, the cloud data center or the ground station, to make decisions on what data to send down selectively from the satellites, right? So adapting these techniques, however, will not be trivial. It will require careful consideration of this type of constraints. Now, you can't tell the satellite from the ground station very frequently what to do because this channel, the uplink, is quite severely constrained. In fact, the constraints are so tight that even TCP acknowledgements are problematic. They can be quite expensive in this context. So this raises another question, which is of how to design efficient, reliable transport protocols. Note that this problem was already known for more than 2 decades. There's even an RFC from several prominent folks in networking about this very issue. However, in the intervening 2 decades, we have learned a lot about transport protocol design. The question that arises is, are any of the new lessons helpful in designing efficient transport protocols for this setting? With that, let's shift to ground station networks. So here again, the demand for ground station capacity is increasing quite rapidly from these growing satellite fleets, but there are a lot of constraints on how we can build and operate ground station networks, where we can place them, for instance. They need, for example, to have large capacity for moving data terrestrially, right, like to data centers. And this capacity is not available everywhere. There's not fiber lines running at every possible location on Earth. So these limitations, again, create several challenges that are worth thinking about. One is, this is the same kind of problem as we already discussed for the satellite side, the challenge of scheduling using the distributed footprint of the ground station network to schedule data downloads effectively. So how do we do that? I think one of the talks, Deepak's talk today, will touch on this problem. How do we resolve the competing customer demands as these ground stations get virtualized, right? So with Azure and AWS both having these ground station as a service offerings, how should they adjudicate between competing customer demands for capacity? Last, how do we design the infrastructure itself? What's the optimal placement of ground stations in a ground station network? There's already a trend towards using data centers, so co-locating ground stations with data centers, but perhaps IXPs, Internet Exchange Points, and cable landing points would also be useful starting points for placing ground stations. So these are all, as far as I understand, open problems for now. Let's go on further to broadband constellations. So here we have thousands of routers zooming about in space at about 27,000 kilometers per hour, making these networks highly dynamic with frequent changes in path structure and the latency of end-to-end paths. This creates several challenges, including across the entire network stack, right? So topology design, routing, congestion control, application performance. I'm being deliberately terse here because the BOPM and Giacomo's talks tomorrow will cover many of these aspects. So I'll focus instead on some challenges that step outside the architecture of the planned LEO constellations. So let's look at the design space using this schematic. So on the x-axis, again, we saw this earlier, is network capacity or market share of some type and latency. So this is just the same schematic we saw a little bit earlier. What I want to add now is another design point in this space where you use multiple types of orbits in the same constellation or same network to provide different types of connectivity. So for instance, you could have a few low Earth orbit satellites, something like on the order of 100 low Earth orbit satellites that meet the needs of latency sensitive traffic. Plus, you can augment these with a few medium Earth orbit satellites, and these serve the goals of throughput from the network. So combining these two, you can build an effective system that might be as good as massive scale in LEO at a fraction of the cost. The only reason this is possible, potentially, is that the vast majority of internet traffic is not latency sensitive in terms of bytes. So most bytes are carried in not latency sensitive traffic, making this kind of strategy potentially workable. So this kind of mixed orbit design is in fact, I think, one of the strategies out there, with the SES being an operator that's exploring this. However, not much is known publicly, and this makes it a nice open direction for research. Another such possibility that uses different types of constellations is to use eccentric orbits for targeted coverage. So eccentric orbits are not circular centered on the Earth's center, but of this type, oblate or elongated. So such orbits, the satellite spends a lot more time over one target geographic area rather than equal time globally. So when the satellite is near Earth, you could potentially use this satellite for low latency traffic. And when it moves farther away, you could use it as a throughput enhancing satellite. And a combination of several such orbits, several such satellites and several such eccentric orbits could provide a good mix of low latency and high throughput satellite connections at all times. So again, this type of mixing could enable systems that are efficient for targeted connectivity in a geographic area rather than global connectivity. I should mention that this type of eccentric orbits were used in military communication systems, but I haven't seen explorations of them at large scale for providing broadband to a target geographic region. With that, let's move out of the new space area and look at more traditional industries and settings. So here again, there are several interesting problems, for example, for network vendors. The ground stations represent a highly unusual operating environment for networking gear, with frequent path structure and latency changes and connectivity changes. And these kinds of connections incur high packet reordering as well as loss as paths change and there are handoffs. Now, this means that there are several opportunities for designing router hardware that operates at these ground stations, and also for control software that controls a distributed network of such routers. One could imagine designing new protocols that maintain connectivity efficiently, taking into account all the routing updates that are happening on the network. One can use the knowledge that's typically not available in networking. In this case, you know quite far in advance what the changes of the network are going to be, except in cases of failure. So the motion-based changes are predictable and known, and those could be used to enhance the efficiency of such protocols. One could also plan traffic engineering, one could plan routes, not just spatially, where you think of what traffic to send on which network paths, but also temporally, what traffic to send on which network paths now and into the future. And you could do this to enable smooth traffic changes such that there are not sudden congestion points from satellite movement causing path structure changes. With that, let's shift to the next industry segment here, cloud or content companies. So here again, the sophisticated operators like Google, Microsoft, and others build custom sophisticated software-defined WAN wide area networking solutions. However, the LEO links that we are talking about are very different from today's WAN fiber links. For the same reasons I mentioned earlier with latency changes, packet reordering, high bit error rates, random loss, etc. So are the software-defined WAN networking solutions deployed out there mature enough to handle these dynamics from these LEO links? Is that the case, or do we need more new work here? I'm leaning towards the latter. That's why this question is posed here. Further, even though you have these, let's say, routing mechanisms and software-defined network mechanisms to enable such multimodal connectivity, how do you best use it effectively for enhancing application performance? How do you select what traffic goes where at any time? This again is non-trivial. Last, there's a potential for value in the cloud operator or content network operator getting a raw, no FEC, no forward error correction link from the satellite network operator and using its own software techniques to do that, depending on different applications' needs for correctness. So some applications might be okay with a few bit errors, and others will absolutely not tolerate them. And taking this control away from the satellite network and doing this in-house with knowledge of the application needs might be another direction to explore. I'll skip over the last one here in the interest of time. So next, let's look at the ISP and telco industry. Here again, there are several new market-based challenges. Two, for example, are that not everyone will want to spend a 500 franc fee on a user terminal for these broadband constellations. Even enterprise customers might not want to send all their traffic to the satellite network because this kind of connectivity will probably be more expensive than fiber. So this raises a couple of questions. One being, could the ISPs and telcos create managed services for enterprise customers such that low latency traffic is selectively transmitted on the satellite network for long distance communication, of course? So these links, as I mentioned, over long distances can be faster than fiber in terms of latency. And there's potential for ISPs to create managed services that integrate them with high throughput fiber links such that applications can benefit from the best of both worlds. Google, Microsoft, etc. can do this for themselves. Most enterprises will neither want to nor will have the capabilities to do this. The other aspect is to try to resell this expensive satellite broadband connectivity to consumers using cheaper last mile technology. So what are the various methods in which this might be accomplished? That might be another potential direction to explore. Next up, government agencies. These LEO broadband constellations provide a new type of broadband offering. There's several characteristics that make it easy to use for providing broadband to a lot of people, but there are also these expense-related factors that we just talked about in the ISP industry as well. However, they do show that the barrier to broadband via space is much lower than one would have expected perhaps 10 years ago. So again, how should governments adjust their policy making, for example, for goals like broadband for all? So how should these new broadband offerings factor into that decision making? Second, is it worth building country-targeted constellations? Is this something that governments should consider to serve their own populations? Lastly, for my own people, academics, all of the above, these are great spaces to do research in. It's all fertile ground. I'll touch on one additional specific actionable item. I've been planning for a while a platform, a testbed for experimentation on satellite networks, SatNet Lab. The name's inspired by the Planet Lab testbed, not to be confused with Planet Space Labs, from whom we'll have another talk later today. The idea here is to start with university sites with equipment, user terminals from networks like Starlink, and use these for experiments, for measurements, to test congestion control, to test application layer performance, and produce methods that improve this performance. While initially I had come up with this idea of the platform for broadband constellations, I think there's actually room for doing this for imaging applications as well. For instance, collaboratively launching nanosatellites for research. So if you're interested in more, please check out this editorial I wrote for SIGCOMM CCR to learn more and get in touch if it interests you. So now let me briefly summarize the agenda for LEOCONN. We have 10 exciting talks, 5 on each day. We'll have plenty of time for questions and breaks. We have budgeted 15 minutes after every talk, except this one, in which we'll keep 10 minutes for questions and 5 strictly break time. We'll also have an industry panel at the end of the day, which I hope will be very exciting and let us engage with our panelists, our speakers from the industry, to learn more insights. I want to close by thanking my co-organizer, Devopam Bhattacharjee, who did a lot of the heavy lifting in making this event hopefully a success. We'll find out by the end. And Ilham Esani, who's helping us with moderation and management behind the scenes. Thank you both. You're welcome to connect with all of us via email and LinkedIn as you may wish. Thanks. So I'll stop here and we'll start with the next talk right away. I'm not taking questions for this talk because you'll have more interesting opportunities to ask questions in the individual in-depth talks by our fantastic speakers, rather than this high-level overview that I presented. But nevertheless, if you should have questions, please feel free to get in touch with me using email and LinkedIn. Feel free to introduce yourself. All right, thanks everyone.
Thank you, Ankit. So let's introduce our next speaker, and then I can start the video because she's ill and she's here, Melissa. So let's introduce. Yeah.
Sure. Thanks, Devopam. So Melissa is a PhD student working at the Network Design Lab here at ETH Zurich. She works on both satellite networking briefly, like you'll see in this work coming up, but her primary area of focus is video streaming optimization. She did her master's before coming to ETH at University of Bologna, where she has experience with software-defined networking infrastructure for optical networks. With that, we can take it away. Unfortunate that Melissa fell sick, but we have this backup video recording that we can play for you. Please go ahead, Devopam.
Hello everyone, I'm Melissa, and today I will talk to you about the outlandish idea, or maybe not so much, of having computing in space. Specifically, I will tell you about the perks of adding computing to low-flying satellites, which are currently being deployed to build a mega constellation to offer internet services. Starlink, Kuiper, and Telesat are some examples of such proposals. Such satellites are meant to be deployed in low Earth orbit. While the first phase Starlink is planning to deploy there around 4,000 satellites, their long-term goal is to deploy there more than 40,000. Our question is really simple. What if we add compute to these satellites? And let's try to unpack these into 2 more specific questions. What can we potentially achieve by moving computing to space? And as I think most of you are wondering, is it really worth it? As we will soon see, we were able to identify some very interesting use cases, and a rough estimate suggests that the cost shouldn't be too prohibitive either. In any case, we think that more in-depth analysis is needed with respect to our current work. But let's be positive. With in-orbit compute, no matter if you are in a town, on a trekking trip, or casually standing on an helicopter in the middle of the ocean, compute will always be available. Now let's look at the first interesting use case. So this is the current deployment of a large CDN in the US. Compare this to their footprint in the African continent and in Middle East. In large part of the world, CDN edges latencies can still be over 100 milliseconds, which largely affects end-user experience. We know from past works that as little as tenths of millisecond difference in round-trip time can substantially affect user experience for web browsing and online gaming. Also, for pervasive applications like augmented reality, latencies beyond few tens of
Sorry about that. So let me again share my screen.
use case. With extremely tight short response time, in the order of magnitude of millisecond. An example is telesurgery. Most of this application depends on data that can be fetched and or processed with extremely tight latency requirement on ideally available and ideally nearby cloud infrastructure. So, are satellites available? Are satellites nearby? Let's see. These are the observer fields of view in different parts of the world for Starlink phase 1. The x-axis represents the panoramic 360-degree view on one observer, while the y-axis represents satellite's altitude. Different color of satellites signify these different shells. The blue shaded regions marks the minimum elevation restriction, such that satellites in this zone are considered non-visible. As we see here, as time passes, even with a minimum elevation of 25 degrees, there are many satellite choices available. More specifically, let's try to quantify the number of Starlink phase 1 and Kuiper satellites reachable from ground location at any time. The solid line denotes the average, while the dashed lines denote the minimum and the maximum over time. For Kuiper, more than 10 satellite servers would be reachable from almost any location Kuiper serves. For Starlink phase 1, more than 30 satellites are reachable from almost every location at all time, usually more than 40. Now that we talk about availability, let's try to quantify how nearby satellites are. The plot shows the round-trip times from a ground location at different latitudes for Kuiper and Starlink phase 1. For each constellation, we computed the RTT from ground location every minute over 2 hours. We use the maximum value across these measurements. We do so for the nearest reachable satellites, as well as the farthest directly reachable satellites. The nearest reachable satellites is roughly within 4 milliseconds at most latitude for both constellations. Please mind that these numbers are computed by considering only the propagation delay, so we expect true latency to be somewhat higher. A huge set of applications, like for example multiplayer online games, involve multiple users sharing the same online environment. The quality of experience of the entire group depends on every user experiencing a low latency connectivity to the server hosting the application, that we will refer as the meetup server. Let's assume we have 3 users in West Africa that want to use a collaborative application hosted by Azure. Let's also assume the user terminals can communicate directly via satellites without any gateway. Even using Starlink LEO constellation to connect them to the nearest terrestrial meetup server, we find the RTT would be as high as 46 milliseconds. On the other end, the RTT to a meetup server hosting using in-orbit compute on the same constellation would be as low as 16 milliseconds, almost 3 times lower. Let's now move to another possible and interesting use case. Many applications like Earth imagery, weather observation, and remote sensing generate their data natively in space. Satellites performing such measurement could produce a large volume of data. To give you an example, a single layer aerial image of contiguous US covering 8 million square kilometers occupies around 55 terabytes of data. Sensing time of such satellites is however limited by the transmission capacity to ground station. Preprocessing the data using in-orbit compute could increase the sensing time and decrease the bandwidth cost of downloading its data and further process it terrestrially. The figure highlights in red the satellite of Starlink phase 1 constellation that are not directly reachable by the 1,000 most populated cities. As intersatellite bandwidth is less constrained than radio downlinks, we could potentially allow the satellites to pre-process data cooperatively and reducing the downlink bandwidth demand. Now that we had a look on some interesting use cases, let's explore the second question. Is it even feasible? We computed a commodity server weight and volume relative to the one of a Starlink satellites. We use a high-end server, let's call it S, with 64 cores and up to 2 terabytes of memory. the overhead in terms of weight and volume would be around 6% and 1% respectively. While the cost is undoubtedly non-negligible, it doesn't sound too prohibitive either. It would intuitively lead to less deployed satellites per launch to an increased mass. Space hardware usually needs hardening against ionizing radiation hazard, but ongoing research hints the possibility of using commodity hardware below the inner banal radiation belt, and instead rely on software hardening. Concerning power, the high-end server S, operating between 225 watts and 350 watts, would consume between 15% and 23% of the satellite entire power budget. This is a large overhead. Possible solutions include, for example, the use of a lower wattage server or equipping satellites with larger solar arrays and batteries. The latter would increase, again, satellite mass. Another related problem is the increased heat generation. Heat is harder to dissipate without an atmosphere, so additional radiators or thermoelectric harvester might be needed. Again, the mass per satellite will increase. Concerning the life cycle of the components, Starlink satellites will have a lifespan of around 5 years, which is slightly longer than the typical data center server lives. Unlike in data center, if an orbit satellite is malfunctioning, it cannot be immediately replaced. However, operators continuously replenish the constellation and maintain backup satellites per orbit. Even with a substantial portion of server failing, a large LEO constellation could potentially continue to provide a useful orbit computing service. And what about cost? Given what we said so far, our current estimate is the satellite server would be roughly 3 times as expensive as a terrestrial data center server. Last but not the least, the dynamicity of LEO constellation poses an interesting challenge. Let's visualize this through an example. If a satellite is now over eastern Brazil, in 6 minutes it will already reach Africa, crossing the entire Atlantic as it moves to the humble speed of 450 kilometers per minute. Given this speed, it is clear that a particular meta server is only reachable by client for a few minutes, after which a handoff is needed. This handoff is different from the one of Wi-Fi or cellular network due to the additional mobility of the infrastructure. Also, trajectories are highly dynamic, but yet predictable. Thanks to handoff, meetup server can expose to client an abstraction which makes them virtually stationary. Operations are then performed at roughly the same location in time by different physical LEO satellites. Given a set of clients at random location on Earth, we investigated 2 approaches to select such physical meetup servers. The naive min-max approach picks the latency optimal physical satellites at each instant. It minimizes the maximum latency across a set of clients connected. Min-max, however, suffers from potentially frequent handoff, and given the dynamicity of the constellation. An alternative approach, Sticky, prioritizes stationarity by planning ahead, leveraging predictable satellite path. It computes a set of meetup servers that provide the latency within 10% of min-max, orders them by the longest time to hand off, and among the top 5, pick one that would result in the smallest latency for handoff to its successor. For the 3 users in West Africa use case, Sticky substantially decreases the frequency of handoff at the cost of less than 10% of latency inflation, while the latency for state transfer to the successor remains similar across Sticky and min-max. To conclude, the mega constellation can theoretically host a sizable aggregate compute, enabling low latency compute access from everywhere at any time. While the pros might be very attractive for some type of application, the costs are non-negligible, but yet not too prohibitive. We know that that can sound like an outlandish idea, but is it so outlandish? Apparently not so much. In recent years, few companies have been taking some exciting steps forward in this direction. Orbit's Edge core mission, for example, is to deliver high-performance orbiting data center to store and process space-native data. SpaceBelt, instead, is building a secure space-based cloud storage network. These companies are indeed moving the cloud to LEO. And you, what do you think? Thank you so much for listening. My collaborators and I are happy to take questions. And in case you're interested in reading more, please check out our 2020 Hotnets publication. Thanks.
All right, thanks a lot, Melissa. So any questions, please feel free to enter your questions in the Q&A interface here on the webinar, and we'll be happy to ask them. Any questions? All right, in that case, we'll move to, we'll thank Melissa for her excellent talk. Thanks a lot, Melissa. And we'll move to the next speaker in 3 minutes. So we have a 3-minute pause. It's important to take these pauses instead of continuing powering through the entire way. So let's do that, and we'll see each other in 3 minutes. All right, we are back. Our next speaker is Deepak Vashisht. He's an assistant professor at the University of Illinois in Urbana-Champaign, which is also my alma mater. Good to see you here, Deepak. His research is focused on mobile computing and Internet of Things systems. He's designed and built and deployed systems that deliver ubiquitous sensing, accurate indoor positioning, enhanced communication capabilities, and new human-computer interfaces. His research on IoT systems for agriculture, I think this is the Farm Beats project. Please feel free to correct me. Our next speaker is, sorry, the YouTube playback on my end. I apologize for that. Deepak's work on IoT systems for agriculture has been deployed across farms in the US, in India, and in Africa. His work has been featured in The Economist, IEEE Spectrum, BBC, MIT News, and several other news outlets. He's the inaugural Microsoft Industry Research Fellow and a recipient of the ACM Sitcom Best Paper Award, the Microsoft Research PhD Fellowship, and the President's Gold Medal at IIT Delhi. It's not better than IIT Bombay, though. Deepak has an undergraduate degree, just a college rivalry, sorry, folks. Has an undergraduate degree from IIT Delhi and a PhD from MIT. Please take it away, Deepak. Thanks for your talk.
Hey, thanks, Ankit, for the really nice introduction. Hi, everyone. As Ankit mentioned, I'm Deepak. I'm an assistant professor at the University of Illinois, Urbana-Champaign. And today, I'm going to be talking about a new approach of downloading data from low Earth orbit satellites. This is joint work with my student, Jay Shinoy, and my mentor, Ranveer Chandra at Microsoft Research. So over the last few years, we've seen a rapid increase in the proposal for satellite launches and the actual satellites being launched. And this has been driven by two main trends. As Ankit mentioned, one of them is the low cost of designing CubeSats, which are these tiny satellites that can be designed using off-the-shelf components for tens of thousands of US dollars. And the second trend is the low cost of launching these satellites into space using ride-share agreements. Because these satellites are tiny, multiple of them can be launched at the same time on a single rocket, similar to how you would Uberpool. So overall, the cost of designing and launching satellites has come down from tens of millions of dollars to, say, a few $100,000 per satellite. And this has been driven by two key applications. One of them is communication, which is to provide global internet connectivity using large constellations of these low Earth orbit satellites. So for example, you might have heard about networks by SpaceX and Amazon that deliver continuous connectivity across the globe using these low Earth orbit satellites. The second application, which I'm going to focus on today, is the one of Earth observation. And essentially, the core of the idea is similar to how you would use drones. So you take pictures from space and you send them to ground stations on the Earth for analysis. The main companies in this space, for example, are Planet Labs, Capella Space, ICI, so on and so forth. In fact, about 45% of low Earth orbit satellites today are meant for Earth observation. And just to give you a little bit of background, these satellites operate in low Earth orbits and go around the Earth, around the poles, and take continuous images. So these low Earth orbits are around 500 to 1,000 kilometers above the surface of the Earth. And they have a period of about 90 minutes. So every 90 minutes, the satellite crosses the poles and then scans a different section of the Earth because the Earth is rotating underneath it, as you can see on the left. And they continuously scan different parts of the Earth and send these images back to the surface of the Earth. The modern constellations of these Earth observation satellites have three unique properties which make them very interesting. One of them is that they operate in low orbits, which gives them high resolution. So as Ankit showed in his beginning slides, the resolution has been continuously improving. And today you can easily get a resolution of sub 5 meters per pixel. And in the next few years, this resolution is going to keep going down or keep getting better. And you might even get a sub-meter resolution in the next few years. The second interesting characteristics of these satellites is their large constellations. So remember in the previous slide, I showed you this single satellite that's orbiting the Earth and continuously taking images. So if I were to ask that satellite to take image of my home, for example, I would get one image every 5 days or every 10 days, depending on the orbit configuration. But as I deploy more and more of these satellites, this frequency keeps going up. And the planned constellations are going to bring this latency from several days to hours and even say sub-minute. And finally, the hardware keeps getting better on these satellites. So you can imagine not just getting RGB or visual imagery from these satellites, but also multispectral imagery, say UV or infrared, or even radio waves. So because of these really nice and important characteristics of these Earth observation satellites, we can see them being used in multiple different applications, not just today, but more and more applications in the near future. So for example, one big application is agriculture, where you can use the data collected by these satellites for precision agriculture and for monitoring events like floods on the farm, monitoring irrigation, and different kinds of events. Another application is maritime tracking, where you can use these satellites to track motion of ships for illegal smuggling, for defense agencies, and you can also monitor the regular ship traffic. For example, on the right is a figure of the increased ship traffic because of the Suez Canal blockage recently. And you can imagine using these satellites for disaster monitoring. Again, on the right is a picture of a forest fire being tracked by one of these satellites. And you can imagine using it for applications like early detection of these events, or for tracking propagation, and assessing the damage caused by these disasters. And this does not apply to just forest fires, but other natural disasters like floods, earthquakes, so on and so forth. So hopefully by now you realize that these satellites are really interesting and they have a lot of useful applications that are going to be used across the globe. But the key challenge for these satellites is getting the data down from them back to the Earth. So each of these satellites is collecting hundreds of gigabytes of data per pass. And as Ankit mentioned, together, it boils down to downloading terabytes of data from these satellites and downlinking it to the Earth. And the challenge is that if I'm an observer on Earth and I have a receiver, I can only be in contact with the satellite for about 10 minutes when it goes from one horizon to the other. And this 10 minutes is also sort of an optimistic estimate, because every time this satellite appears in the horizon, I don't see it for 10 minutes. So from a networking perspective, this is a really tough problem, because you have to download hundreds of gigabytes of data in a very small amount of time, which is just 10 minutes, over a link that's really long. It's a 500-kilometer long link, and you need to download this really high volume of data in a short amount of time. So today, to solve this problem, we designed these large, massive, complex ground stations that cost multi-million dollars in investments. And each of these constellations operates about 4 to 5 such ground stations located close to the poles of the Earth. It makes sense. You want to use as good as components as you can for this downlink because you want to eke out every last bit of SNR from this link. So you want to use these massive dishes and really fancy equipment for each of the components on these ground stations. But this ground station architecture, which relies on these massive ground stations and 4 or 5 of them located close to the poles, has multiple shortcomings, which I'm going to talk about today. So the first problem is latency. So for a satellite to download this data, it has to be in contact with these ground stations. And it comes in contact with one of these ground stations on the order of several hours. So even though you may collect an image in sub-hour or sub-minute, to download this data and give it to your user, you have to be in contact with one of these ground stations. And this latency can be very high for latency-sensitive applications like disaster management. If you're tracking a forest fire, you want to get this data to you as soon as possible. Scaling these ground stations is capital intensive. So if you have more and more of these Earth observation satellites being deployed, you need more ground stations to download this data. And this can be very capital intensive. And finally, failures in these ground stations can be disruptive. So imagine if one of these ground stations has a hardware failure or has a bad link because of bad weather conditions, then you cannot download data to them anymore. And this data is either delayed or lost. So today, I'm going to talk about a new proposal for designing these ground station architectures, which we call the distributed hybrid ground station design. This design has 3 interesting properties. One is that we replace these massive ground stations with these tiny dishes and low-cost ground stations that can be deployed all around the globe. So instead of thinking about these massive dishes, think about a tiny dish that can be deployed on your home. Second, this design is distributed. So you take these tiny ground stations and you deploy them across the globe. You distribute them geographically. And the third, this design is hybrid. So a lot of these tiny ground stations are receive only. They don't transmit any data. And this is because the crucial bottleneck in low Earth orbit satellites and for Earth observation satellites is the data downlink. You don't have as much data to send upwards. It's mostly just getting data from these satellites that they're measuring back to the ground. And the key question that I'm going to ask today is, can a network of these tiny ground stations outperform or even match the capital heavy huge ground stations that I showed you earlier? So on high level, this is what the architecture looks like. So you might imagine these tiny ground stations spread across the globe and either helping or augmenting the existing massive ground stations that we saw earlier. Naturally, such a design would be more fault tolerant because even if some of these ground stations fail, there are other ground stations that will keep up the network. There'll be lower latency because instead of waiting for you to see a ground station every few hours, you can see a ground station right below you all the time. And more importantly, the architecture is hybrid in the sense that most of these ground stations don't need to transmit, which reduces regulatory burdens and the cost. So as an example, when Amazon launched their ground station service, for a long time, they could not transmit any data because of FCC regulations. So one way to think about this distributed hybrid ground station design is to see it as a parallel shift that we saw in the satellite domain, where we moved from these massive satellites to these low-cost CubeSats, but large constellations of these. So we're proposing a similar shift in the ground station architecture, where we move from these massive ground stations to these tiny ground stations, but a lot of those, so that the aggregated capacity makes up for single ground stations. However, such a design has multiple technical challenges that we need to solve as networking researchers. The first challenge is we need to do rate adaptation without feedback. So when a satellite talks to this ground station and it does not have any feedback, it needs to figure out what the ideal rate to transmit this data is. It needs to schedule these satellite ground station links. Given that we have so many satellites and ground stations, how do we define which satellite talks to which ground stations? And from a networking standpoint, also, these receive-only ground stations cannot really transmit any acknowledgements. So how do we know what data has been successfully downloaded and what has not been yet? So let me start by talking about rate adaptation. So let's say there's a satellite. It's going over these ground stations. During its path, the link quality between a satellite and a ground station can vary by 10 to 20 dB in terms of SNR. And for people who are unfamiliar with SNR, SNR is signal to noise ratio of the signal, and the higher, the better in general. And this link quality variation depends on the elevation of the satellite with respect to the ground station. It depends on the weather. Bad weather can actually decrease the SNR by 8 to 10 dB for X, Ku, and Ka bands, which are the typical frequency bands used for these Earth observation satellites. And it also depends on the equipment. Depending on your hardware, you might see different link quality. And if you have a hybrid design where a lot of these ground stations do not transmit, they cannot send any feedback about this link quality, which means it is very hard to do rate adaptation. And the reason we need rate adaptation is that if you use a very low rate to transmit this data, which is way lower than what is supported by the SNR, then you waste opportunity to transmit this data to the Earth, where you could have transmitted more data, but instead you're sending less data. And if you send at too high a rate, your packets get lost because your SNR cannot support this. And as a result, you don't end up getting no data back to Earth. So what we need to really do is to do rate adaptation, but without getting feedback from these receive-only stations. So to give you some intuition into this problem, I'm just going to show you a trace of SNR for a satellite ground station link over X band, which is around 8 to 10 gigahertz. So on this plot, the X-axis is time. And as I said, one contact lasts about 10 minutes, and the Y-axis is the SNR. And this is a standard, it's like a typical plot that we saw on this satellite ground station link. And there's some interesting things to note here. So in the beginning, as you can see, the SNR goes up, which is kind of understood because the satellite starts from one horizon, reaches almost overhead, and goes down. And when it's almost overhead, it is supposed to have the best SNR because it is the closest to me as a receiver. But then we saw this kind of weird dip almost at the top. And this is typically caused by environmental factors. Let's say if there is an obstacle, or the design of the satellite is such that one direction is supported less, or there is a multipath effect, which is caused by reflections in the environment. And another interesting factor is that if we look at the same measurement, but on a different day when there was a little bit of rain, the SNR goes down by 3 to 4 dB, even though the rain intensity is not that high. So what we want to be doing is to estimate this SNR so that we can predict the ideal rate that you want to be sending your data at. And this link quality, or the SNR, has 3 different components. One is the propagation loss due to distance. So as the distance between the satellite and the ground station changes, the link can become stronger or weaker. The second one is weather-related losses. So if it's rainy versus cloudy versus clear weather, that can have significant impact on your SNR as well. And the third one is the location-specific losses caused by reflections or the antenna design on the receiver itself. So what we can do intuitively is to predict this distance using orbit parameters, because the satellites go in fixed orbits. We can predict exactly what time a satellite will be in contact and what its distance will be. The second factor is the weather loss, and we can predict that a bit using weather forecasts. So if you have a prediction for rainy weather, you know that this is going to be a lower quality link than when there's a prediction for clear weather. And finally, we can calibrate for these multipath and hardware losses because they're sort of constant across time. And if we can combine these losses, we can estimate them and create a data rate factor. So in reality, we use a machine learning model to predict this link quality, and I'll talk about the results of this model later. But on a high level, what this model does is takes as inputs the orbit parameters and the weather forecasts. And it passes it through two different networks. So we're using an ensemble model of a random forest and a neural network. And both of these networks predict together the SNR, or the link quality, of the ensuing signal. So what this helps us do is that it can help us predict the SNR, or the link quality, of the connection between a satellite and ground station at a very fine time granularity. And we can do it without getting any feedback from the ground station itself. So this allows us to operate with ground stations that do not have any transmit capabilities and yet optimize the link quality to its best. Okay, so the second challenge. So now that I figured out how good a link between a satellite and a ground station will be, even before I have actually used that link, I need to schedule satellite ground station links. So today, if you have a small number of satellite and ground stations, this problem is sort of trivial, because not multiple, no two satellites will ideally be in contact with the same ground station at the same time. But as the number of satellite increases, there are bound to be conflicts. Different satellites may want to talk to the same ground station, and the same ground station may talk to multiple satellites at the same time. So it needs to pick which ground station needs to talk to which satellite, because most often than not, a ground station can talk to only one satellite at a time. Okay, so now we can estimate the link quality before a satellite is actually even in contact with the ground station, based on the algorithm that I just described to you. And we can use that to assign weights to each of these ground station satellite links. And these links, these weights can be tweaked to optimize for different kinds of metrics. So we can try to optimize for latency, we can try to optimize for throughput, or even geographic restrictions. If we don't want satellites from, say, one country to download data in a different country, we can optimize for that as well. So this problem in itself is a standard bipartite graph matching problem, where you identify a good bipartite matching given two sets of nodes. But there's another technicality which makes this problem even more interesting theoretically, which is that switching links from one ground station satellite to a different ground station satellite pair is not free. It takes some time. For example, the dish may have to rotate from one satellite to the other, and as a result, you might suffer some disconnection in the middle. So you have to pay a cost for switching from one link to the other, which means these matchings are not time independent. And theoretically, what that leads to is an NP-hard problem. And for people who've worked in data center networking, they can sort of map this problem back to data center scheduling problems as well, or data center switching problems, where circuit switching leads to, penalties for data center throughput. So we designed this new algorithm that acts a penalty for switching. And because an optimal algorithm is not possible, we designed a greedy algorithm that can sort of get a good approximation. And the idea behind this is the following. So let's say we start with this network where we have different links with different weights that are possible. And we choose these blue links, and we decide to not go with these orange links. So every satellite chooses a ground station, and they're transmitting to that in some kind of optimization function. But when we're scheduling the next time instant, we assign a cost to links that don't exist, so that switching costs are taken into account. And we optimize this function again using this algorithm called the Hungarian algorithm that can find the maximal matching within these reduced costs. This algorithm is well known, and it converges in k cube time, where k is the maximum number of satellites and ground stations. What we haven't done yet is identified the approximation guarantees for these for the greedy algorithm. So that's what our next step is going to be. Okay, so finally, the last challenge that I talked about is about acknowledgements. So we said that because a lot of these ground stations are receive only, how are we going to get acknowledgements back to the satellite, and how does the satellite know what data has been successfully received at the ground and what has not been? So I'm not going to go into the details of how we achieve this, but on a high level, the idea is that we have a few transmit capable stations, which can be the massive ground stations that we saw earlier, or just any other ground stations. And these transmit capable stations can be used to relay acknowledgements from these receive-only stations. So basically, the way it works is that the receive-only stations will relay the ACK to the transmit capable stations. And when the satellite is in contact with this transmit capable station, this data can be uploaded to the satellite. And at this point, it can discard any data that has been successfully received or retransmit data in its next iteration. So on a high level, this is how the overall system operates. So there are a few transmit capable stations and a lot of these stations that only receive data from the satellites. So when a satellite comes in contact with a transmit capable station, it can communicate with it and identify a plan of downlinking data at these other stations. So it includes the data rate it needs to use, the amount of data it can send, and where it has to send it. And as it passes over these ground stations, it can download this data to these receive-only stations. And they're all connected at the backend to either the cloud or a backend scheduler where this data can be collated and collected together. Okay, so now I have described some of the key components of this distributed ground station design. I'll talk about some of the experiments that we have done to validate and the measurements that we've done to evaluate such a design. And of course, there are more details in this work than I've been able to speak about today. So I'm happy to chat about them later or point you to some of the research papers that we've written on this topic. So for the first set of experiments that I'll talk about is using real-world measurements. So for these measurements, we used 5 different ground stations in different parts of the United States, and we got data from 4 different satellites. So there are GPSS, SNPP, Aqua, and Terra. So these are government satellites used for different kinds of sensing. The links that we tested were in two different frequency bands. One of them was in the X band, which is 8 to 10 gig, or 4 of them were in the X band, which are 8 to 10 gigahertz. And one of them was in the Ka band, which is around 16 to 20 gigahertz. And these measurements were performed across 1 month in 2020. So these are the locations of these different ground stations that we tried out. And as you can see, they're spread quite across the globe. So the first result that I'm going to show you is how accurately can we predict the link between a satellite and a ground station using the machine learning algorithm that I described to you earlier. And for this result, I'm going to plot on the x-axis the error in the SNR estimation in dB. So as I said, SNR is the signal to noise ratio and dB is on the log scale. And the y-axis is the CDF, and CDF is the cumulative distribution function. And I'm going to plot 2 results. One is for DGS, which is what we call the distributed ground station design. And the second one, which will be the red curve, is the curve using an ITU model, which is a standard model that's used for search link predictions in the past. So this is the result for DGS. So this is the result for our algorithm. And using our algorithm, the median error in SNR is about 0.4 dB, which is really small for any kind of data rate errors. And in contrast, if you were to use the standard ITU models, the errors would be much larger, around 3 dB or more. So what this means is that we achieve about an order of magnitude more accurate predictions in this link quality estimation. When we convert these numbers to data rate, because that's what we are interested in, the data rate errors are 6.25% for DGS. So we are kind of close to the accurate data rate prediction. We undershoot or overshoot it by at max 6.25%. And the ITU median errors are 41%, which are much larger. So there's 2 points that I want to make here. One is that this link prediction algorithm is a core contribution of this line of work, and it's very important for operating with these receive-only stations. But more importantly, this link prediction is important for other applications beyond this DGS design itself. For example, in planning your satellite constellations and ground station placements, and we can achieve that much better using the models that we designed. So the second experiment that we did was for large-scale emulation, and clearly we couldn't deploy, let's say, like hundreds of ground stations, hundreds of these tiny ground stations across the globe yet. So we used data from the SatNox open source ground station network. So SatNox is amateur ground station network operated by mostly ham radio operators, which are hobbyists who deploy these ground stations. They listen to signals coming from satellites. And these ground stations don't really operate in the Earth observation bands most times. They're being operated at a much lower frequency, which is why we have to do an emulation, and it's not a real experiment. And we emulated 100 GB data per day per satellite, which is 26 terabytes total for the satellite set in SatNOG. So we used about 259 satellites and 173 ground stations for our emulation. And the benchmark was that we use only satellites and ground stations that have had active downloads in the last week for this result. And for a baseline, we used 5 massive ground stations, and each of these ground stations has at least 10 times higher throughput than the smaller base stations that we deployed in this SatNOG network. So I'll highlight 2 main results of this evaluation. So the first result is around latency. That is, can we get lower latency if we are to distribute the ground station capacity across the globe, as opposed to concentrating this in these big ground stations that are located around on the poles? So for this result, the x-axis is the latency in minutes, and the y-axis is the CDF. And I'm going to compare like the baseline 5 massive ground stations, DGS, which is these 173 tiny ground stations. And for fairness, we're also going to compare DGS 25%, which uses just 40 ground stations instead of the 173, just reduces the number of ground stations to 25%. And at that level, DGS 25% has less overall capacity than the baseline, which has these 5 massive ground stations, and each of them is 10 times as powerful as these DGS ground stations. So this is the latency for the baseline. So as expected, the median latency is around an hour, and the 90th percentile and the 99th percentile are much higher, about 4 to 5 hours. But if you were to use a distributed ground station network, which distributes the capacity from these centralized ground stations to these tiny ground stations, you can get a much lower latency. The median latency is around 19 minutes, which is much less as compared to this massive the centralized ground station architecture. But more importantly, even if we reduce the number of ground stations in DGS to just 25%, which has less capacity than the baseline, the latency does not increase that much. It's still within 25 minutes on the median. And even the 90th percentile and the 99th percentile are much better. So this reduces the latency by about 5 times with the same capacity that's distributed across the space. So the final result that I want to talk about is on backlog. So essentially, this measures how much data remains to be downloaded on the satellite at the end of each day, or at the end of each cycle. And the x-axis is the data backlog. So of the 100 GB data that it wanted to send, how much of it still needs to be sent from the satellite. The y-axis is the CDF. So one way to look at this is in terms of queue sizes at the satellite, for example. And for the baseline, this comes down to about 10 GB median, and it's way higher on the 90th percentile and the 99th percentile, around 25 GB. But if you were to use this DGS architecture, the DGS 25% architecture, again, this backlog goes down. This is again sort of expected because the capacity is distributed. The satellite can find more chances to downlink its data. So this design is still a very early work in this direction. There are many open questions, and I'm going to conclude by talking about some of these. So the first question is around satellite power. If you have distributed ground station architecture, the satellite needs to turn on its radio more often, which means it has implications for how the satellite utilizes its power, and it needs to redesign that. The second question is economic model. So if you want to design a distributed architecture, who operates this architecture? Is it operated by independent entities, or is it centralized? And what are the incentives to deploy this architecture? Because ideally, you would want these distributed ground stations to serve multiple different constellations. And then what kind of economic models are being factored into this? And the third question is edge computing. So as Ankit mentioned earlier, and as there's been a lot of discussion in other communities, we want to bring some of this edge computing research into the ground station design itself. So for example, if a ground station gets an image of forest fire versus a forest where nothing is happening, it ideally needs to prioritize the image coming from the forest fire and alert someone sooner, rather than wait for processing all of this data in queue. And sometimes it might actually take several hours to get the data from the ground station to the cloud. So you want to reduce that, or at least prioritize data that is more important for latency sensitive applications using edge computing on the ground station or edge computing on the satellite itself. And finally, I talked about these ground stations that can talk to one satellite at a time. But there's new designs of ground stations coming up that can do beamforming and talk to multiple satellites at the same time, or use new kinds of materials called metamaterials to talk to multiple satellites at the same time and beamform in different directions. So if you incorporate them, then the scheduling functions change, and we're yet to look at that. So some of the work that I talked about today is going to show up in the upcoming conference, ECM SIGCOMM 2021. So I'd really encourage you to look to check that out. And if there are any other questions, I'm happy to take them now. Thanks a lot.
Thanks a lot for the great talk, Deepak. There are indeed several interesting questions here in the chat, so I'll raise them one by one. Nishant Shastri asks, can you comment on the process you used for doing your experiments on JPSS and others? Did you have to talk to someone in the US government? Is it widely available? How do you get your hands on it?
Yeah, so this is a good question. And to be honest, like, this was largely done by my student Jay. But the way we approached this was we talked to several ground station operators, and these are like government operators, university operators who have like already established these ground stations and are communicating with these satellites. So so that's what we did, and we were able to get not the data itself, but the analytics or the telemetry in terms of what's the SNR over time, over a month for these different ground stations.
All right, thanks. Manish Kumar Isar asks, will the LEO satellite carry two different transmit antenna modules for communicating with large and small ground stations? Is that the case?
No, not really. Like it's just so the ground stations are capable of listening to these like basically to the same transmissions. It does not have to be a different antenna.
All right, sounds good. Another comment from the same person is 1 month's data seems somewhat small for data rate prediction because it might not capture all the different weather patterns that are possible over a longer time span. Were you able to verify your ML model on a larger data set?
Yeah, so there are two aspects to this answer. One is that we had a lot of geographical diversity in our data set. Like it's going from like Wisconsin to Hawaii. Like so basically, like for non-US folks, like Hawaii is this like kind of like moderate climate. Wisconsin is kind of like a more cold, and Antarctica is again like a cold climate. So they're very different like weather patterns available in the data set that we already have. And some limitation also comes from the fact that this is the amount of data that we had when we did the analysis. But we're definitely looking to do a bigger scale analysis by deploying our own ground stations. We're deploying one on campus here at UIUC, but we'll have like much larger data set to test this on. But we are confident that there's like a lot of weather variations within the data set that we have.
All right, cool, thanks. So actually one follow-up question before I move on to the next one. So did you also have any insight on what was the problem with the ITU models? Where are they lacking, or sort of techniques to retrofit them back with insights that you might have learned?
Yeah, so that's a really good question, Ankit. I think the difference is that ITU models are generally not meant for this like second level predictions, right? They want to do some kind of aggregate analysis for planning a satellite ground station link. It's not as if it's meant for like this like second level like real time predictions because that's what we're going after.
I see.
So I think on that aggregate it works fine. It's just that when you try to do it like at a second level, you need like more fine grained analysis.
All right, great, thanks. Another question is from Sukirna. By the way, folks, if you would like me to introduce you, I can also state your affiliations in the chat if you put them together with your question. So question from Sukirna, since your setup already uses a high cost ground station to uplink the acknowledgements, wouldn't it make sense to just use the same station for downlinks, making the downlink only stations redundant? Unless, of course, the downlink to uplink bandwidth ratio is very high. Have you looked at how high this ratio should be to break, for a model to break even?
Yeah, so I think like Sukina like kind of answers like their own question in the sense that the downlink to uplink bandwidth ratio is actually very high. As Ankit, you mentioned, right? This is 1000x. So typically in a traditional ground station, the uplink is a few kilobits per second, operating on the 2 gigahertz S band, which is again like a shared spectrum. So it's not very high. And the X band downlink can go up to gigabits per second. So as you can see, this is like several orders of magnitude different. And that's exactly the reason why a model like this might make sense, where you have a lot of like downlink capacity spread across the globe. And the second distinction is the latency. So even if you say that you have like almost exactly the same bandwidth available in this like big station versus like 10 of these small stations, the 10 of the small stations offer you a much lower latency and much higher fault tolerance. So if one of these links is like down because of weather or like a hardware failure, it like the cost is not that high. And one example that I like to think about is like supercomputers versus data centers, right? Like supercomputers are these like high performing computers, whereas the data centers are like distributed computing, but like together they perform much better. They have like much more flexibility. So that's one way to look at this design.
Great, thanks for the answer, Deepak. Thanks for the questions, everyone. I see no more questions in the Q&A, but if there are some, please feel free to chime in now. Meanwhile, I have one question for Deepak, which is, so you download to these distributed ground stations, and how do you get the data to the data center? I think you mentioned something towards the end about this in your talk, but I didn't quite get. So for example, if you have a home user, or I don't know what kind of connectivity these guys are on, right? So the distributed ground stations. So if they have tens of megabits per second, and you're trying to send tens of gigabits per second, this is still going to amount to quite a long time transferring that data back to a data center, right? So how do you bridge that gap?
So today we haven't like really looked at that analysis, to be honest. Like we focused on getting the data to the ground stations themselves. But there are two directions that we're exploring. One of them is the edge computing piece. That is, what kind of edge computing can you run on the ground station itself? And the way it's and the reason, like the way I think I like to think about it is that, you know, there is also this idea of like doing edge computing in space on the satellites themselves. But inevitably, the edge computing on the satellites is going to be like less like computationally heavy and less like it is going to have less resources and less flexibility. But the edge computing on the ground station itself can be more compute heavy and more it's going to be like have more compute and more flexibility. So we want to explore that a bit in figuring out how to optimize the uplink to the cloud itself. So that's and the second bit of this answer is that every ground station in this model does not get as much data as you would think, because this is like not these massive ground stations. Like this is kind of distributed across these ground stations, so it might still be feasible. But we haven't done like a really like foolproof analysis to comment on that yet.
That's also a good point. Thanks. Meanwhile, there's another question here. Prabhat Raman asks, you mentioned 100 gigabytes of download in a 10-minute window. With your DGS optimization, how often do the SNR parameters get optimized in this 10-minute window?
Yeah, so in our case, we optimize it almost at the second level, that every second we optimize like what the SNR is going to be, and we sort of try to predict that. So one kind of caveat that I didn't mention during the talk is that under prediction of SNR is kind of okay, like you lose a little bit of data rate, but over if you're too optimistic about your SNR prediction, that has like a higher cost in the sense that you might lose like almost all the data that you got. So there is that bit of it. So we try to like shoot for under prediction than over prediction. Is not like a standard machine learning model where like every error is the same. Like some errors are more important than the others. But yeah, so in terms of time granularity, we almost do it at like a second level.
Great, thanks, Deepak. So I think we'll close here. We should force these 3, 4, or 5 minute breaks between talks. Otherwise, everyone will be zoomed out. So we'll see you in 4 minutes with the next talk. Thanks, everyone.
Thanks, Ankit.
Hi, Yves.
Hi, Deepak.
Hello.
Hey, Yves, long time.
Great talk.
Thanks.
I feel bad because I will talk about big antennas now. Checking, you can see my screen, the slide.
Yes. So this is still the PowerPoint, but if you kind of do a full screen, it should work.
All right, it should be okay now, right?
Yes, perfect.
Yeah. Looks great, thanks. Alrighty, folks, let's welcome our next speaker, Yves Pitch. He's a principal program manager for Microsoft Azure Space under Azure Special Capabilities, Innovation and Infrastructure Group. Conveniently, the acronym is ASCII. He leads a range of space-related products, including Azure Orbital, which enables satellite operators to communicate to and control their satellites, process data, and scale operations directly with Microsoft Azure. Prior to that, Yves was responsible for Microsoft Global WAN, internet infrastructure, and software-defined networking technologies. All right, Yves, please take it away. Thanks.
Thank you. Hello, everyone. So I'm Yves Pitch. I'm product manager in the Azure Space team. And today I'm going to talk about ground stations virtualization. So you may wonder what's the relationship between ground stations and Microsoft. And well, back in September last year, we announced a new industry practice called Azure Space. So Azure Space includes a set of new products, solutions on partner ecosystem, offering an integrated cloud and satellite experience. So it spans areas like global connectivity, or how can we connect anyone's data from anywhere on planet and off planet at any security level into our clouds. So that's the global connectivity part. But we also have areas of investments around analytics marketplace, on how to leverage space on geospatial data, Azure solutions in space, and of course, emulation and synthetics for simulating satellites. One of these products we announced last year as well is referred as Azure Orbital. So Azure Orbital is in the Azure Space portfolio. sometimes referred as ground station as a service. So Azure Orbiter is a managed service that lets you, the satellite operator, communicate to, control your satellite, process data, and scale your operations directly into Microsoft Azure. So as part of Azure Orbiter, we are deploying multiple satellite ground stations in our data centers, enabling a variety of scenarios, including Earth observation, remote sensing, and global communications, cutting across a variety of industry segments, remote mine, oil, energies, and defense, and whatnot. So with Azure Orbiter, our goal is to enable our customers and partners with a vibrant space ecosystem, from modem vendors, data processing and AI partners, as well as third-party teleport providers such as KSAT. So we are indeed deploying like these ground stations, and you can see the first one we announced last year was in Quincy, Washington. These are like 6.1 meters antennas supporting X, S, and UHF bands. So kind of the opposite of what Deepak talked about. Even, of course, over the course in the coming year, we plan to build many more ground stations and also integrate with the partner networks. So basically what we do with Azure Orbiter, we also interconnect our antennas with the network of other ground stations, such as KSAT, Viasat, and USCI. The idea is to allow customers to schedule a contact time against any antennas. So let's look at the high-level architecture. So as a customer, you can onboard your satellites on Azure Orbiter using APIs or the Azure Portal experience. Once onboarded, customers can schedule contacts with their satellites using Microsoft and partner ground stations. So with Microsoft ground stations, we leverage virtualization by digitizing the radio signal at the ground station and processing the signal in the cloud using high-speed software modem from our partners. You have the two here mentioned, Kratos and Emergence, and more to come. We consider these high-speed software modem as virtual network functions, and they are especially optimized for Azure. The processed data is then delivered to the customer's virtual network, where it can be further processed and enriched using multiple other Azure services, including compute, storage, AI, machine learning, cognitive services at scale. Orbiter can also provide a fully digitized wideband raw signal, 500 megahertz wideband, raw IQ, to the customer for processing unique scenarios. So in that scenario, we just send the raw data or raw IQ straight to the customer virtual network on the right side, you can see on that slide. Now, for the purpose of today's talk, I will focus on one important design element, which is the software radio. So we decided to virtualize the modem. In our ground station, we only have the antenna and a digitizer. That's it. Now, what does it mean from a performance and scale perspective? How does it fit into the overall cloud architecture model? And that's kind of the challenge I would like to cover in today's talk. So let's look at multiple flavors of deployments and the things we looked at. So if you look at the conventional deployment model, right, we use physical, dedicated hardware-based modem and deploy them in the ground station. It has few challenges that you can see listed here. It starts from the supply chain, import-export issues, spare management, maintenance. But when we designed Azure Orbiter from the get-go, we wanted to have an open platform when our customers can decide the modem of their choice. And obviously, we cannot deploy multiple flavors of the modem in the same ground station. That would be very expensive. So what we did, we partnered with modem vendors to make them run as virtual functions. So now, in the next set of design, that's what we use today in our Azure Orbiter platform. As I said, we have the antenna, the digitizer, and then we run the modem as virtual network functions. So modem vendors, we partner with them, we co-engineered, and they can leverage our Azure accelerated networking stack, which is basically FPGA-based networking data path accelerated by DPDK. And we put a bar of 500 megahertz wideband. Now, by doing that, now the challenges we had with the classic deployment model, now we get lots of benefits. From a supportability perspective, it's very easy to add new waveforms, such as DVB-S2/X. The supply chain is highly optimized. It's much easier to deploy, update, on bring new capabilities on the fly. So by doing that, now we give the customer choice. The customer now can pick the modem from a marketplace based on their own requirements. Maybe they already work with few modem partners. So in that case, there's no disruption for the customers. By doing that, we also introduce challenges. The challenge number one is that the digitizer is still a piece of physical equipment. The modem is picked by the customer, but how do we enable seamless interrupt? Can I have a digitizer from vendor one and a modem from vendor two? So we had to standardize our data exchange protocol, and we adopted VITA 49.2. We defined the requirements for a modem partner to onboard into our orbital marketplace. And it turned to be a very successful approach. I will show you a demo in a few minutes where I will show interrupt between two different vendors. So our approach for building an open platform is really around standardization on interoperability. Without that, it's very complex to build a multi-tenant platform, open platform that would meet the needs of all the customers. The challenge number two is kind of related to some physics, is like the distance between the ground station and the compute location. So with the current deployments we have in flight, the compute location is very close to the ground station. So we have the antenna, the data center is just on the other side of the world. So we don't have any issues with latency, on fiber capacity, and whatnot. So all good. But even though we have lots of data centers in the world, we have situations where there's no choice, the ground station is far away. And we are in a remote location, and the fiber availability in the market is pretty poor in that case. So no way we can transport raw IQ over a low capacity, long haul network. And that was the challenge we had to address. So what do we do? So are we back to square one? Do we need to deploy hardware modem in a remote location? Can we still get the same benefits than the modem virtualization I just talked about? And in fact, the answer is yes. So the virtualized modem we co-engineered with our partners can run into an edge compute platform. So when you say cloud platform, it doesn't necessarily mean running compute into a massive, like 520 megawatts Azure location. Customers can get the same benefits at the edge. So think about edge compute as devices that bring the compute, storage, and intelligence to the edge, right where the data is created. So basically, they are local extensions of Azure. So by doing that, you can still run. You can still run in the same way. You still get the same benefits of virtualization, right? So what we need to do is now deploy a generic hardware platform called edge compute. So we have multiple flavors. First party type of what you call first party edge compute is basically you lease the hardware. So you go to the Azure portal, define your requirements, and you get equipment to your location. That's the lease model, but you also support what you call edge HCI, which is like you pick your own OEM vendor and define what kind of hardware you want, knowing that this will be certified to run and support the Azure platform. So now supportability, upgradability, and scalability are the same than running in the data center. And that's key here because I raised the issue about import exports, on spare management and whatnot. In that case, if I have a generic hardware platform, I can drop anywhere in the world it becomes kind of straightforward, right? And much easier for the customer and for us to kind of manage the ground stations. So these are the two challenges: interop on making sure that whatever we do in a massive cloud data center, we can do it at the edge. Now, what next? We are obviously looking at a bunch of new optimizations. So of course, we do have partners, modem vendors who are using FPGA. Not all, but some of them are doing that. So by doing that, we also partner to make sure that they can bring their own FPGA stack into the cloud. So we do support high performance compute using GPU and FPGA Xilinx based platform. And our customers can just transfer the code they have on the FPGA stack into the cloud, run it in a very optimized manner, and the same code again can run at the edge. That's a key benefit of our FPGA stack. More security, so that's key. So we introduced last year a platform called Azure Confidential Computing. Basically, it allows you to isolate your sensitive data while it's being processed in the cloud. So we leverage VMs using Intel processors with Intel SGX, it's called software guard extensions. So basically, modem vendors can build a secure enclave-based application. And think about the enclaves as a secure portions of the hardware processors on memory. So there's no way to view the data and code inside that enclave, even if you use a debugger. So if untrusted code attempts to modify the content in this enclave memory, encrypted memory, the environment gets disabled and the operations are denied. That's key. Many of these scenarios are targeted for government type of scenarios. And for those who are familiar with the red-black concept, I think it's key that if you look at the full end-to-end chain, there's no way to kind of interject in the middle to capture some kind of data. So that's important. So encrypted memory and build your own enclave, isolated enclave in the processor. And the last is about agility. So DevOps is key here. So I talked about edge compute. So we want to make sure that regardless of the modem locations, we want to have elasticity and make sure that our design fits to the concept of distributed architecture, which is tricky because at the end, it's an RF signal that you have to scale out. And there's lots of complexity if we want to build a distributed architecture behind that. So lots of investments in making sure that we can scale out instead of scaling up, just to adopt the cloud concepts. So going back to the first challenge. So interop was our challenge number one. As I said before, we need vendor diversity. And on top of that, we know that each mission is unique and customers have special requirements in terms of modem and waveforms and whatnot. So our approach was to build a standards-based exchange, leveraging Vita 4902, virtualized radio transport. So what I will do is show you a demo. And in that demo, I am using two devices. One is a modem from Emergent called SatRack, and one is a quantum radio from Kratos. And basically, I will use one modem to transmit and modulate, and one modem to receive and demodulate. Right. So, so let me switch to the demo. And so here, this is a view of our Azure portal. So I will skip the details. Here, there's a name, that's the name of my colleague. Here, you have the name of a resource group, right? Think about this resource group as a logical container that holds related resource for a solution you develop. So basically, in that container, you can put VMs, storage accounts, anything related to your project. So in that resource group, I have two VMs. One is, you can see here, the SatRack from Emergent VM, and the second VM is the Kratos VM. Right. Switching to so now what I do, I click on the SatTrack virtual machine, and now you can see the details about that virtual machine. So two things to look at. So check for the demo, check the private IP address here. This is 10.0.1.11. And I am in the same resource group. So this VM, I picked from that resource group, and this is my SatTrack VM. If I go to the next tab, we'll go to the same thing. We'll go to the Kratos VM. So same thing. So I have my resource group here, and check the IP address here, 10.0.1.5. So now what we'll do, we'll go to the third tab, and we'll show the Kratos QRadio modem. So I'll pause. So so basically now we go to the QRadio modem, and you will notice that we have configured the modem for a very simple mission. This mission will have the Kratos modem transmit a modulated signal through the Emergent modem in a Vita 49-bit stream, and we'll demo how we do the demodulation on the other side. So the first mission is very basic. Oops, sorry, I click on the wrong side of the video. So I'm going back to where I was. All right, so we do have configured for a very simple mission. BPSK modulation type, 50 kilobits, modulation rates, and you can see the transport rates here, and you can see on the right side the transmit channel emitting at real time. So I'll pause here now. That the other side now is the demodulation part, which is the Emergent. So on that side, now we are receiving the signal, and the expected rate is 50 kilobits per second. So in that modem, I will move on the video here. So you can see the received rates, so receive rates, data rates at real time. And if you go to the next step, I'll put here, the most important things to look at is the modem is fully locked. The signal is being received, both carrier lock and symbol lock have been achieved and persist during the mission. So you can see it also in the zero lost count for both of the logs. So what we'll do a reset of the stats, and you will see that there's no lost. So here reset on the right, and now I just receive the packets and no loss. So I again click on the wrong one. So basically here, which is pretty unique. So we had to work with Kratos on one side, Emergent on the other side, to make sure that we align on the Vita 49.2 specifications we did. And now here I'm showing like a transmit between two different vendors and the receive on the other side. So what I will continue with the video, and basically in our demo now we show the receive side on Emergent, and now we are also doing the same, and we'll do the transmit side on the Emergent. So here you can see the transmit BPSK. You can see the rates being transmitted again. Going back to the model overview, the channel specification, and this is the packets, and the target remote location, which was 10.0.1.5, which was modem configuration, the Kratos one. Now Kratos one, if you look at the receiver channel, you can see the status. And you can see the carrier lock and the lock state here, and you see that the bit pattern stats here. So bit pattern in 23, no loss, we do resets on the. So now what I showed you is basically transmit and receive between the two modems. So we have worked very closely for the last few months with both our great modem partners to define the specs and partner with them to implement that in their VNF to achieve a successful interop. This is a unique differentiator for the orbital platform on the ecosystem, but we believe that this will also serve more the space industry moving forward towards a standards-based approach to benefit the industry more broadly. So we don't want to restrict that to our platform. We want to make sure that this is adopted across the industry space. Going back to the presentation. So the next part I was talking about is can we run the same solution at the edge, right? So now if you look at the edge flavors, here you have multiple edge flavors. So the ones in that slides are what you call first party hardware equipment. So this is a lease model. So you go to the Azure portal, you can lease that equipment. It can be 1U box, FPGA, 24 core or plus, depending on what you need. Could be a rugged device, could be a bigger form factor, depending on what you need. And now, basically what we are doing is like we're moving the modem virtual functions from the cloud to the edge. So now that ground station is composed of the antenna, the digitizer, and commodity hardware running, virtual functions. Now, that makes sense. Now, it makes sense, especially when the fiber availability is not at quality, in a remote site. And there's lots of scenarios where we need to have these antennas kind of far away into north latitudes or south latitudes, far away from data centers. So I will show you a different demo. And the demo I will show you is a demo of Azure Orbital Stack Edge. So in that demo, what I have, I'm back to the Azure portal, and I have a resource group, Azure Orbital Stack Edge for my demo. And I can add this resource called Azure Stack Edge, which is basically my physical device running in a remote location, right? So basically, I have the view of each of the edge compute locations I have. Here I have only one. And what I will do, I will click on that resource. We'll do a pause here. So now I clicked on my resource. I can see a status online. So I can see some health information about that device. I can see some information about, capacity. You can see this is a spec for that device. So this is Azure Stack Edge Pro. It's a GPU device. So we'll continue. I click to on the properties and pause here. Now you click on the properties of that box, the name, capacity, information about that device, and so on, and click next. Here now you can see the physical ports available on that box. So I have access to the ports information. So we use the jump box to access to that machine. That's because of our lab setting, but you can see the IP address of these physical ports. And one of these ports will be used to access to the virtual machines. So the virtualized platform. So that will be my port number 4. So we'll go to the next step. We'll show you how it looks like. Right. So now what I did, I will pause. It was a bit fast here. So basically, now what I'm doing is we are going straight to the device itself. So now I'm logging to that device that is remote. Now in that device, I can see the images we have set up for that demo and the VMs that are running on that image. So now I am on a remote site, so you can see the IP address. That's kind of the jump box address I'm using to access to that device. So this is the admin console for that device. Same status, same type of information, have the health information, have the state, have information about the network and whatnot. Moving on. Click on the network again. You will see that I have the same ports that I showed on the other admin console. Now, my compute is set up to use port 1, as you can see here, enable for compute. So this port will be used to access to my VMs. So what I will do, I'll look at the virtual machines that are running on that VMs. I have 3 images. Going back here, doing a pause. So you can see I have 3 images set up for that, that machine. One is Quantum RX, and one is the bunch of other VMs, but the ones we are looking here is Quantum RX. And out of that 3 images, I have bootstrapped 3 virtual machines, which is basically the Quantum RX solution. Moving on, these are my images. You can see here. Clicking on the virtual machines, QRX. And now what I can do, I can just simply access to that VM. So now I have clicked on that special VM, Quantum RX. You can see the OS type, the status, the type of the VM. This is 16 virtual CPUs, pretty low, and I'm running Quantum RX service here. Going back here. And now what I do, I log into that machine and access to my Quantum RX admin console. So you can see now still the same IP address used by the port number 4 I showed you, logging into the admin console. And then you can see here that the same demo I had before. Now in that case, I receive, if you look at the receive channel on the configuration, so it's a different demo. So it's an OQ PSK demo, it's a very light demo. But you can see that it's exactly the same experience. So now me, either as a cloud operator or the customer, could have exactly the same experience, but now that machine is running in a remote site. Right. So that's what I wanted to show you, is like really show you that we can achieve the concept of transformation of the ground station into a digital platform through virtualization, but getting the benefits of DevOps, model, getting the benefits of OpEx model as well, because in that case, I just need to bring VMs, into that hardware platform. Whether I'm running these VMs in the cloud, like the data center, or in the remote site, it's kind of ubiquitous. So it's the same kind of story. So that's kind of what I wanted to show you. Going next. Just to summarize the talk here. So basically, we do believe that virtualization works very well in this type of scenarios. It brings us operational agility, supply chain agility, which is very important for us. The idea is to be able to deploy fast. Don't get stuck on spare management, on supply chain, type of issues. For us, it's much easier to deploy commodity-based hardware. It's an OpEx model, kind of very straightforward. And now, if you want to move that to the cloud, I think there are 2 key aspects. We do believe in standardization. I talked about Vita 49 as one way to standardize the data transport exchange. But there are a few areas where we believe standardization is key. You'll have more talks, during the day or tomorrow, but we'll likely talk about 3GPP and whatnot. So there's a few things that will make sense to adopt in order to kind of streamline the adoption of the cloud for satellite services. So standardization is key. Performance compute scenarios can be available anywhere, so that's also important. And from a security perspective, we also believe that cloud can bring lots of benefits and increase the security bar. It's not about decreasing. I shared with you a few scenarios about confidential compute, but there's tons of scenarios where basically when we move some of the assets through the cloud, basically it's much harder to attack from a security perspective, in the sense that these virtual machines are running into a virtual network. A virtual network is kind of a private boundary in the cloud, highly compliant with the security standards, very hard to control by the customer. And we do support, encryption at rest and transit using customer key and platform key. So these are things we can bring to the table. And I think if you combine cloud concepts with the ground station concepts for the purpose of satellite communication, we can get lots of benefits. And the last benefit you get is also a massive global network, which is fiber. The fiber, used between data centers or at the edge of our data centers, we are talking about, terabits. The unit is not megabits or gigabits, it's terabits, and aggregate capacity, we're talking about petabits. So the scale is so different. Knowing that the amount of data we have to transport keeps increasing. That was what Ankit started with the first session, but the idea is to make sure that if we manage to bring the data to the cloud, now you get also the benefit of the global network. So that's the end of my session. So open for any questions.
Thanks a lot for the talk, Yves, particularly the demos. That's not common. Thanks a lot for that. So there's a question here from Joel Bush, who works at Switch. For folks that might not know, Switch is an ISP in Switzerland that primarily serves educational enterprises, so ETH, universities, that kind of work. So the question is, Joel expresses surprise that a modem can be virtualized. Does the fixed digitizer hardware not inherently limit what kind of modulation your customers can run, since they don't have the analog signal available for soft decision demodulation? Is that not a limitation in practice?
So you always have limitation as soon as you rely on some physical equipment. You're right, and that's an area of investment as well. But however, the bar is I mean, it's much easier for us to manage. I think what we're trying to solve is really like being able to address custom waveforms and modems requirements from our customers. But you're not off from your questions. You have some limitations, but I think for us these are much easier to address. At some point, it's the digitizer itself. It's also an element in the chain that we'll have to address. It's a great question. Yeah.
All right, thanks for the response, Yves. So one question from my side. Hopefully, meanwhile, other people pipe up with their questions. So you mentioned that there are sites where the ground station is far away from compute and you're using edge locations and such. But for the small amount of data after processing, or reduced amount of data after processing that you have to move back, what kind of connectivity are you using? Is it still fiber, just smaller quantities, or smaller bandwidth, or what is it?
So good point. So with Azure Orbital, we have our own ground stations. In that case, we always use fiber. So there's no discussion whether we are far away or not. It's our fiber. That's a design principle we use in Azure. Is like each time we have an asset somewhere, we control the communication end to end. When it comes to a third-party ground station, you have multiple flavors of connectivity. So if we believe that there's a need to exceed some thresholds, basically we also bring our fiber. Or in that case, it's not what we call dark fiber, it's we lease fiber. The capacity requirements are much lower. So when we bring our fiber, the bare minimum is 100 gig. In that case, we take 10 gig. It's still a lot for some of these markets, but we tend to always bring our own fiber for from a security perspective, also for the Spirit to own the communication end to end. But for some scenarios, we use internet VPN if there's no need to justify some amount of traffic. So it's case by case. but the default principle is we tend to bring our fiber. Yeah.
All right. Thanks, Eve. Thanks for the talk, and thanks for taking the time for questions as well. So there's another question in the chat now. Sukirna, who has been at ISRO and now works for Truveta, does Azure Orbital also intend to support fleet management operations like ranging and special requirements for launch operations and station keeping?
Not yet. I think it's a scenario we are looking after, but there's no such plan for now.
All right. There's another question about. Could you please elaborate on your statement about supply chain agility? What does this mean specifically?
Well, if I have to export equipment to some markets, we'll not name the markets, but some markets are more complex than others. It takes time. Sometimes you may be stuck into what we call imports of rights. Basically, your equipment stays in customs for a long time. So the more diverse type of equipment that you have, the more complex it is. So we do have our own supply chain for data centers and classic like commodity hardware equipment, which is streamlined. As soon as we add exceptions into that, it's just more complex. So we want to keep supply chain super easy. The challenge is mainly a time to deliver the equipment, in some specific markets. We don't have that issue in in the US or Europe, but as soon as you go out of that, it sometimes is tricky. Yeah.
Great. Thanks for the responses, Eve. All right. So, folks, we'll stop here. We have 7 minutes till the next talk. Let's take a break, and we'll see you all in 7 minutes. That's 1/4 past the hour. Thanks.
Thank you.
Hi, Catherine.
Hello, can you guys hear me?
Yes, we can hear you. So
Great.
you can already share your screen and your video as well. I mean, video you can do later, but maybe test the slides and everything if you want.
Perfect. Yeah, let me pull those up. Okay. Oops. Okay.
Yes, I can see Google slide.
Let's see if I can get it into presentation mode. That'll be more helpful.
Sure.
Perfect. There we go. Okay.
Yeah,
Let's do a
perfect.
quick
This
video
works.
test.
Yep.
Oops. And now you can see me as well.
Yes.
Great.
Perfect.
Okay.
Everything
I'll
works?
turn my video off here for a second.
Sure. Thanks.
Hi, everyone. We are back from the break. And now we have the pleasure of hosting Catherine Monson, who has just finished her tenure as the CEO of KSAT Inc., which is the American headquarters that support the Kongsberg satellite service, that's KSAT, the world's leading provider of ground station communication and Earth observation services. KSAT's uniquely located global ground network is used to provide rapid data delivery for new and legacy space satellite missions. Thanks for joining us, Catherine. Please take it away.
Great, thank you. So I first need to apologize. I have some tropical decor. I am actually tuning in today from Hawaii, where I'm on vacation with my husband. So pleased to be able to be here with you all. And I guess that means that we're doing a full 12-hour time zone split. If many of you are joining from Europe, it is just the morning here in Hawaii. So I have the luxury, as Ankit mentioned, of being able to take a step back. So I am at a unique point in time where I, as of Monday, have resigned from my position at KSAT. Unfortunately, I'm not quite able to share what comes next. I'll be able to share more about that in a few weeks. So Ankit, I'm sorry that I can't do the big reveal here today. But I do want to take this opportunity to be able to take a step back and take actually a much higher level approach to space communication services. So Yves, very much enjoyed your presentation. Always great to see how you at Orbital, Azure Orbital, are thinking about this market. As many of you know, KSAT has partnered with Microsoft. So Yves and I have been working closely over the last few months. So it was great to be able to see more of that technical deep dive. In contrast, I do want to take kind of a much higher level approach. So for those of you who are just getting into space communication services, coming into this industry, maybe from a different domain or discipline, hopefully this can serve as a bit of an anchor for the talks both today and then on into tomorrow. I am really hoping to make this an active dialogue, particularly for those of you joining in the evening. It is much more rewarding and fulfilling for all of us if we can make this an open dialogue. So I do really encourage you to ask questions in the chat as we go. Ankit, if you can jump in and make sure that I see them, I would like to answer those slide by slide so we can create more of a dialogue as we go.
Absolutely, I'm happy to do that. Thanks, Catherine. So I'll just interrupt at an appropriate point and raise a question.
Perfect, that sounds great. So a bit about my background. So KSAT, as Ankit mentioned, is the world's largest provider of ground communication services. So KSAT is a company that has over 50 years of heritage. It goes all the way back to the first European Space Agency program. So where KSAT is headquartered is a place called Tromsø, Norway. So it's at the very top of Norway. And that location was chosen because back in the 60s, that was the location that was the highest northern latitude that did have reliable communications infrastructure. So the European Space Agency built the Tromsø satellite tracking station there, and it provided service to that first European spacecraft. So there's a lot that's changed since that time period, but I do want to kind of start in that early time period so that we can anchor where we are now. So way back in the Apollo program, way back in the beginning of the space race, actually, we had these huge aperture antennas. So for those of you who are antenna nerds like me, you can probably name all of these. So we've got a Goldstone antenna from NASA here on the far left. We have another NASA antenna that's actually part of the Deep Space Network in Canberra, Australia, here in the middle. And then this one on the far right is still used actually to track launches coming out of Wallops. So that's also a NASA asset. So one of the things that you've just heard me say now 3 times is NASA. So ground comms, when it was first done, was the project of governments. So there were not commercial companies that were building these antennas for their own use. There were certainly private contractors who had government contracts from NASA who were building and maintaining these assets, but they were government furnished equipment for government missions. So as you can see, and we don't have a lot of scale here, but we do, I guess, have a small building here and a building underneath these two. You get a sense of really how big these antennas are. So these, the one on the far left is a 70-meter antenna. So by contrast, most of the antennas that KSAT operates today, by pure numbers, if we think in numbers of antennas, not in numbers of passes or in data, pure numbers of antennas, probably half of the antennas that KSAT operates today are smaller than 5 meters. So we're talking about almost over an order of magnitude of scale difference here. between a 5-meter antenna, or actually a 3.7-meter antenna, which is the KSAT Lite network, which is used for our small sat constellation support, all the way to a 70-meter antenna. So one of the things that people often ask me is, okay, well, what's new about this? Why is it a good thing that we've gone from so big to so small? It just seems like we're doing the same thing we did 60 years ago. So what have we been doing the last 60 years? So one of the things that's helpful to point out is that there is a huge, it's not quite an exponential growth curve, but as you look at increasing the size of an antenna, the costs do start to go up very quickly. So just an order of magnitude, as we're starting to think here about, let's say, a 3.7-meter antenna, roughly the cost of building that antenna, including all the infrastructure, the foundation, we're talking, depending on the location and how hard it is to build there. So there's obviously a difference between building in the Los Angeles area compared to building at the North Pole or building in Antarctica where KSAT operates stations. But we're talking about $500,000 up to about $1 million to build a smaller asset. When we look at these 70-meter antennas, we're talking about hundreds of millions of dollars. When they were built, tens of millions of dollars, but even to build a 20-meter antenna today would cost anywhere between $5 to $10 million. And that's just the antenna itself. That's not any of the foundation. So we're also looking at a pretty large increase in cost, both to build and then obviously cost of ownership. These antennas are quite expensive to maintain as well. So, I do think that that's an important piece of the puzzle. My dad actually just asked me a couple of weeks ago, he said, why are we going back to the moon? Why haven't we been there every year since we went? And I think the really important piece here is around cost. So it cost the United States 2% of the GDP to run the Apollo program. That is not a level of expenditure that would be sustainable to do year after year after year unless you have some real gain and benefit for the people of the United States. So the fact that we're going back to the moon with more of a commercialized approach, I think, is the real changing piece here. How do we make space sustainable? Yep, awesome. I'm going to respect the fact that I asked for interruptions. Ankit, over to you.
Sorry, so before you move off the slide, there's a question from Manish Kumar. Sir, what's the approximate lifespan of these antennas?
Ooh, that's such a good question. It really depends how you think about lifespan. So obviously all of these antennas have had quite a lot of work done to them since they were originally built. That is one of the big questions though, is at what point does it make sense to try to start to build a new infrastructure versus continuing to repair an old infrastructure? So a couple of case studies that we could look at. There's a fascinating antenna that's actually in Ventspils, Latvia. So Ventspils was the location of one of the KGB intelligence, satellite communications intelligence units during the Cold War. So when Latvia gained its independence, this land was given over to the Latvian government, and there was a huge, I believe it's a 30-meter antenna that the Latvian government inherited. It was built sometime, I believe, in the 70s. And they, for a long time, didn't know quite what to do with it until there was a big campaign 10, 15 years ago to try to turn this antenna into a radio telescope. So the university said, hey, if we can put money into this antenna, we can maybe use it for scientific purposes. But when we're thinking about a 1970s era technology, the antenna, there's nothing digital about this antenna. So, the entire mechanics of it are vacuum tubes. So very, very early computing that was built into this system. So the idea of thinking of the antenna as only just that parabolic dish, which, is its own mechanical engineering challenge. There's a whole lot of things, within the feed. We have electrical engineering best practices have changed quite a bit since the 60s and 70s. Computing technology has obviously changed quite a bit. So all of those interfaces that would allow you to use the antenna as a helpful asset have seen technological advantages. So I think that's one of the challenges when we think about the building new versus maintaining old. Is at what point is the technology so outdated? Do you decide that you need to just start from fresh because you can't get spare parts for vacuum tubes anymore? There's no way at a certain point, once you've exhausted, all of the folks on eBay who are selling these antiquated technologies, there's no way to buy them anymore. So that's actually such a good question because it's a big question right now that's being asked by the United States Air Force. So the Air Force is essentially trying to make a decision internally about at what point does it make sense to build new antennas or new technologies for the Air Force Space Command Network, which is referred to as the AFSCN. So let's actually come back to that point when we get to the technologies of the future, because I think that's the other big question that all infrastructure companies or infrastructure users think about is if you do think you have to build fresh, when is the right time to do that? Because there's always new technology coming up as well. So you want to make sure that you time it so that you don't build something that in 2 years is going to feel antiquated if there's a state change in what's technologically available. Such a good question. Please continue to ask questions as we go. Truly, it's more fun if this is a dialogue. So again, back to this slide, when we're thinking about how it was done before, the big take homes from this slide are huge scale, which means huge expense. And the only folks who can afford that huge expense are government actors. Okie doke. So, we talked about what was done in the past. Fast forward 50 years. What are the options today? So we've got a couple of different things that are represented by images on this slide. So let me start with the one that's closest to me, which is if we look down here in the bottom right-hand corner, this is Svalbard Station, or what is sometimes referred to as Svalsat. Shameless plug, there was a fantastic New York Times article about KSAT last week. So if you want to learn more about Svalsat, you can Google Svalsat in the New York Times. So Svalbard Station is the world's largest ground station, single ground station. There are over, there are over 100 antennas now on the plateau. So we talked about the fact that KSAT has its origins at the very first European satellite, and that was because it was a very high northern latitude. So 20 years ago, through a great partnership with folks at NASA and what was Lockheed Martin at the time, there was a project that said, okay, there's this archipelago that is another 2-hour flight north of Tromsø. It is at 70 degrees latitude, which is a bit of a crazy thing to think about for most of us, given that most of us don't even live in the Arctic Circle and now we're solidly hours of travel time above the line of the Arctic Circle. So this extremely high northern location, they said this would be an excellent location for satellite ground communications with one exception. And Yves mentioned this as well. There's no communications infrastructure. So sure, we could get a lot of data to this archipelago, but once we got it there, how would we get it off and back to folks who don't live in the North Pole? So this really audacious project was started between the folks that I mentioned to run a fiber line from mainland Norway all the way up to Svalbard. So that program was hugely successful. Svalbard now has fantastic communications infrastructure. So KSAT operates this world's largest ground station at this northern location. And I guess one piece that I did not specifically say, but let's take a pause and talk about why does it matter to be so far north? So many satellites, particularly those who have Earth observation missions, so they're trying to look at a very, any place on the Earth in a given day, particularly missions that are trying to do change detection. They want to have a very similar angle of light and a similar angle of image on that location day after day after day after day. So that makes it easier to train a computer model to say, okay, what has changed from this image to the next image? So the way I sometimes would explain this, to my family, folks who are not in the space industry, it's a lot harder to have a photograph of someone's left ear, their right ear, the back of their head, and then try to say, if you're looking for the compliment of your hair looks nice today, you kind of want the image that shows the subject consistently. So that's essentially what all of these Earth observation companies are trying to achieve with the sun synchronous orbit. So essentially what that means is the satellite is going over the poles and it's in its ellipse and the Earth is rotating underneath that satellite. So what that means is that because the satellite is going from the South Pole to the North Pole, and for satellites that are in this low Earth orbit, so a sun synchronous orbit is a low Earth orbit or a LEO, that satellite is going to go over the poles 14 times a day. So Svalbard, being as far north as it is at 70 degrees, is able to see all 14 of those sun synchronous orbits. So what that means is that we're able to have every 90 minutes communication with the spacecraft. So it is the only satellite ground station on Earth that is able to see that satellite every single orbit. So that's why SvalSat is so important in the industry. And that's also why there's been such tremendous growth, is that missions have taken advantage of this ability to have really regularly planned duty cycles, because they know that they'll have that contact opportunity every 90 minutes. So the model that SvalSat operates under is ground station as a service. So KSAT was built 50 years ago to do ground station as a service. And I laugh with tongue in cheek. I did live in the Bay Area for many years, so I am a fan of buzzwords as much as the next person. You know, the as a service is really the label that's come out of the software industry into the space industry. Really, much of the space industry has been an as a service model, because if we go all the way back to the previous slide and we think about the folks who built those antennas for NASA, those are government contractors. So it's a private company that serves the government market. And that is, you could say, construction as a service or space system management as a service. So actually the space industry, because we have so many subsystems, so companies that specialize in communications or specialize in launch, most of those companies are service companies. So you could say that ULA is launch as a service, or SpaceX for that matter. So the ground station as a service is a very traditional model. So many governments, many companies rely on companies such as KSAT to provide ground station as a service. For sake of full inclusivity here, KSAT has competitors. Those competitors would be the Swedish Space Corporation, SSC. In the US, there's Atlas, there's RBC Signals. Let's see, there's Leaf Space that is based out of Italy. And then there are folks who have been new to this market, who've come in from other, technological bases. So Amazon has announced their AWS ground station. And then obviously Yves has just spoken about the Azure Orbital platform, which works with other space companies to provide this integrated platform. So the ground station as a service is a very common model. People tend to use that model because it does create a specialization and an economy of scale. So let's talk about both of those separately. So the specialization aspect, really, it looks at the idea that, I often said when I was at KSAT, it's not that the folks at KSAT are, incredibly smarter than other people. There are incredibly smart people at KSAT. But the reason that KSAT can be so effective and keeping high proficiency rates is because the company has been around for 50 years. So it's not that folks didn't make mistakes. They just made those mistakes 50 years ago and learned from them then. So we have a legacy of performance that we're able to build on to provide this excellence of service. So I think that's something that really does matter in the space industry, because we are talking about highly technical domain expertise and very niche expertise as well. So if we're thinking about satellite ground stations, all sorts of silly things can go wrong, let alone the really, fancy things that people often think would go wrong in the space industry. And I'm kind of laughing here because if we go to the photo that's actually directly on the top right, this is a Spire ground station. So I was the head of ground stations at Spire before I joined KSAT. So this is one of the ground stations that my team built. I believe this one is Utah, just looking at the mountains behind it. And so if you see the kind of long pokey thing on the far left of the image, that's a UHF antenna. And you see each of those elements, which are the little sticks that are attached to the central rod. Each of those elements is quite small. So very non-glamorous things can happen, like a pigeon can sit on one of your elements and it can bend your element. And all of a sudden, your operations team is looking at the performance of the antenna and saying, we have huge signal degradation. What the hell is happening? Is something wrong with the spacecraft? And you look back through the logs and your team can spend hours trying to troubleshoot what's possibly happening between the space to ground communications link, only to go back on the security video and see the pigeon sitting on your antenna. So I laugh because those are the types of things that folks often don't think about when running a ground station network, is that you can have all sorts of things like a satellite anomaly that you need to troubleshoot, all the way to pigeons that can cause problems for you. And that's really the difference in a company that provides this as a service versus potentially having a university that's operating a ground station to help students learn about the types of things that can go wrong, or the types of things that you need to manage and be proactively accounting for. So as we're talking about Spire, Spire is an interesting example of a company that does a hosted model. So this antenna is fully owned by Spire. The hardware was designed by Spire engineers. Each of those components is an off-the-shelf. So kind of the buzzword of 5 to 10 years ago was the COTS model, or the commercial off-the-shelf. So Spire did not build any of these antennas. What they did do is they figured out how to buy the right things off the shelf to combine them to build a system that worked to speak to the Spire satellites. And the reason we made those decisions, oh, yep, Ankit, go ahead.
Sure. So since you're on the slide with at least 3 different geographies, desert, mountains, and the Arctic. So there's a question from Manish Kumar Isar, who's from Hughes Network Systems. Are there any floating ground stations?
Floating. Are there any floating ground stations?
And
yes, in terms of boats. I'm understanding now. There are. So actually, if you think of I think the best example that folks might be familiar with is if you've ever seen when SpaceX lands the boosters on the drone ship, those are, in some ways you could say that they're floating ground stations, because they are tracking the booster as it's coming back, it's deorbiting. And it is on a ship. There are absolutely many maritime systems that exist on big cargo ships. So if you think about all of these overseas routes for the team that is living and working on this cargo ship, they have their professional needs, so they need to navigate, they need to be able to figure out what the weather is going to look like so that they can navigate around bad weather. They need to plan their ports of call. They also have personal needs. So they are folks who have families that, if they're going to be at sea for weeks at a time, they want to be able to take phone calls, video calls. And so those networks are, antennas that exist on the ship. Often they're actually quite sophisticated systems that allow the antenna to counterbalance the movement of the ship so that it can maintain lock. And those are typically geo satellites. So they're looking actually at a satellite that's in a geostationary orbit that's a fixed point. And that's a little easier to control, at least the satellite is not moving relative to Earth. So that you really just have to maintain kind of and I'm not a maritime person, so it's kind of the movement of the boat. I'm sure that there's a technical term for that. So there are floating ground stations. It is not as common to do a floating ground station for the purposes of just moving data from space to Earth, because then you have the same communications backhaul issue that Yves was talking about. So once you get it to a ship, unless you are planning to use the data locally on the ship, you would then have the same problem of trying to get it, back to wherever your user group is, probably terrestrially. I think there could be an interesting, there's kind of an interesting model in the future as we start to think about another buzzword, the Internet of Things, as different things are networked to each other. It is potential that we could use ships as part of a kind of a multinodal network. But at this point, the use cases aren't there to really make that a common, there's no common adoption of that as an infrastructure. Yeah, good question though. Thank you for asking. So if we're looking then again at kind of the different models, we talked about the as a service model. We were on Spire, which is the, build your own hardware, but then what we call it is a hosting model. So the actual antenna infrastructure is owned by the company, but it is located at a place that can provide that primary infrastructure. So a place that does have, good communications infrastructure, so that networking backhaul, that would have stable power, that would typically have redundant power as well, because you really don't want, if there's some type of power outage, that you're going to lose connectivity to your satellite from that location. So the Spire model is really the hosted model, which is also used by folks like OneWeb. So KSAT, for example, hosts a lot of the OneWeb antennas. So OneWeb owns the antennas and hosts them at Svalbard, among other locations. If we move then to the top left, we have a planet antenna, and I understand that Kurthika is going to be speaking next, so I don't mean to steal her thunder in any way. So my good friend Joe Brew and his team built this antenna, which is a beautiful orbital systems antenna. Nope, this one's actually a CGC. So this antenna is located in Keflavik. It's just outside of the airport in Iceland. And this is a good example of antenna that Joe and his team, they procured land outside of an airport in Iceland as a company that was based in San Francisco. So they had to go out, they had to figure out, okay, where can we buy land in the world that's going to have that good terrestrial backhaul, that's going to have the power and redundant power options. The piece we didn't talk about yet is licensing. I think Eve started to kind of get towards some of these regulatory questions. So Eves was speaking more on the supply chain aspect. So when you're going to be bringing in a lot of pretty sophisticated niche electronic equipment into countries, you end up having quite a lot of regulatory aspects. So import-export becomes an issue. It is, and I say this with hope that we can change it together, it is almost impossible right now to build a ground station in India without being an Indian company, because of the concerns around electronics import. So it's very hard to get your hardware approved to be imported into India. So I do think there are good folks who are working to help address that issue. But again, we're such a niche industry. You know, I just mentioned that even the competitors of KSAT, and you can count them on one hand. It's such a small group of us who are working toward these problems that, typically these problems are not forefront in the eyes of the government unless they have a stated desire to increase their space presence and their space investment. So Joe and his team did quite a lot of work to build this antenna in Iceland, because for every location that you can build an antenna, from personal experience, you probably said no to 10 that didn't meet the criteria. So it takes quite a lot of work to go around and do a site survey. During that site survey, you have to deal with the spectrum usage in the area. So that's the other component of regulatory. So there's one piece that's the hardware. The other piece is actually the radio frequency usage in your area. Jamming is what it's referred to when it's typically a malicious intent. Interference, though, even when it is just two folks who are trying to use the same spectrum, not aware of each other, the impact is still the same. If you have a really loud transmission that is right next door to your ground station, sometimes even if it's off band, if it's a high enough power level, you're going to see signal degradation on your antenna. So at Spire, we actually did build a ground station in a location where we later found out that once a month there was an emergency beacon that would happen in that local area that meant that we couldn't use our UHF for that day. Each business then needs to make the decision of, is that enough of a problem that you need to pack up and move away, or is that something where you just know you're going to have essentially a planned outage that day for that particular location? But because radio frequency is such a local issue, and particularly on UHF. So one of the big problems with the issue that we had at Spire was that this was our UHF, our ultra high frequency. The UHF antennas are extremely wide beam. So the wide beam width means that even if you have, even if you're pointed due north, tracking a satellite that's coming up overhead, you can still have a loud power transmission that's due west. You're still going to have issues because of the wide beam that antenna is capturing in its surroundings. Part of that is actually a feature, not a bug. So it is helpful when working with small satellites to have that wide beam width, because it allows you to still capture signal from a satellite, even if it's in a full tumble. So the UHF was very helpful during the early small satellite development, because if you had problems with your ADCS, you could still get a signal lock. So the model that Joe and his team went with is actually, I think, a very hard thing to do, because it does require a lot of work from the internal team to vet sites to be able to move forward. And then as we kind of start to move toward the future here, working around our kind of counterclockwise circle, if we look at the bottom left, this is a model I'm quite excited about. So this is actually the hosted payload model. So you may say, well, this looks like a satellite. What is it doing here on the picture of antennas? And it's really the idea of moving away from thinking about ground as a service in such a limited fashion as only providing access to an antenna, but instead starting to think, okay, what is the point of this satellite mission? What are we trying to do here? Okay, if we're trying to collect data about the Earth, maybe we can host our camera or we can host our sensor on a satellite that already has a communications infrastructure. And that allows us to start to share some of the cost of ownership. So I really think that this kind of communications as a service is really where we're headed, moving away from the specific tool, which is an antenna that allows us to talk to satellites, and thinking much more holistically about, okay, how do we get data from where it's collected to the people who need to use it? So that takes us into the future. Oh, go ahead, Ankit.
This sounds like a good transition point to ask this. So Shadi Nogabi, I believe from Microsoft, is asking, how many satellites can a ground station serve simultaneously? What is the downlink or uplink bandwidth you can get from a ground station?
Such a good question. So let's take those two questions separately. So when we're looking at these are parabolic antennas, parabolic referring to the shape of the reflector here, or the dish. Each parabolic antenna, for the most part, only speaks to one satellite at a time. And that's because for S and X band, the entire point of this parabolic shape is to be able to really focus to get a really narrow beam width. So that allows you to speak to one satellite. To be technically correct, you could potentially speak to different satellites that were in the same location. So if you have two satellites within the beam width of the antenna, there are quite interesting things you can do with split spectrum that would allow you to use that parabolic antenna to have more than a one-to-one relationship. But at least speaking from the KSAT experience, the use cases that we have are 99% speaking one antenna to one satellite at a time. So not every satellite is going to track that full kind of LEO 12-minute or 10-minute overhead. Sometimes with the data rates that we can support today, you may take a 2-minute pass, you've completely downlinked everything on the satellite, and then you can move to the next. So that's particularly effective for folks like Hawkeye 360 who fly in a cluster. So we may not need 3 antennas to track all 3 of the satellites in the cluster. We can sometimes do 2, 2, and 2 and still get everything within the time that they're overhead. So the question about bandwidth is much more controlled at this point in time by the space side radio. Ground technology, because we have much easier operating environments, right? We don't have that SWaP-C or that size, weight, and power cost trade-off. So if you hear SWaP-C, that's what that stands for. We're able to make things as big as we need to be able to make it work. Whereas on the space side, those radios, are very much a function of the mission scope. So how big is the bus? How much power can the bus provide to the radio? And therefore, how much power can the radio then transmit down to Earth? So the bandwidth, the data rates are much more of a function of the space side radios than the ground. Ground is typically quite a bit more flexible. And then when we're talking about bandwidth, that's typically a function of the regulatory environment. So what is the spectrum that is allocated for the space to Earth, Earth to space, fixed mobile allocation within the S or X or Ka bands? Great question.
Catherine, just a note on time. We have about 8 more minutes before we should take a break.
Perfect. So the infrastructure of the future is much more about multi-nodal communication, and that matches what we've seen in the terrestrial world, as well as just networking in general. So if we look at the bottom right, this is an image from NASA, and this is about optical communication. So I do think that we're going to see quite a bit more optical communication. We're just right now on the kind of turning point of moving from optical as something that works in the lab to optical as something that works in the real world. So many companies are working, and I believe there's actually a gentleman tomorrow from Mynaric who will speak specifically to the optical communications infrastructure that they're developing. They're obviously one of the major players in that optical development. So I'm quite excited about optical communications because it is a way to have even higher data rates. And I'm laughing right now because it does look like this laser in the bottom right hand is speaking to me here in Hawaii. So that's convenient as well. If we look here to the middle picture, this is the use of a multinodal network to be able to build infrastructure for the moon. So NASA is not the only government agency planning interesting things for the future. This is the ESA Moonlight architecture. So at KSAT, we were very excited and continue to be very excited about working with SSTL on the Moonlight initiative to be thinking about different architectures for speaking both to the front side of the moon as well as the back side of the moon. And then if we look to the far left, the top left, this is an image from the Space Development Agency. And really what this shows is a way of using satellites in a chain to do a satellite relay network. So folks like Iridium have been doing this for many, many years with an RF relay chain. The relay chain of the future will almost certainly use optical. So folks like SpaceX Starlink are also trying to develop this technology. So if you hear ISL, inter-satellite link, that is typically what that means. So the inter-satellite links over optical. So, what's driving all of these changes? It's really the commercialization. So if we go all the way back to the beginning, the NASA era in the 1960s of the Apollo program, the only folks who had, billions of dollars to spend on a space program were great powers. So folks like the Soviet Union, folks like United States, we're still seeing that today, that many of the space activities that are frontier technology are supported by NASA, by ESA, by ISRO. So I want to give huge credit to the Indian Space Research Organization. They have done some pretty amazing things in the last 5 years, and actually even more credit where it's due. The PSLV vehicle is, the small sat revolution would not have happened without PSLV. So these nations have been able to support space programs, which has then led to kind of a foundation of a space industry that is now being supported by venture capital. So the major change is in volume. As we've seen more space companies, we've seen economies of scale that allow more things to be possible because we take a really high cost or capital investment and we can share it among more actors and more users. So that's the real story with ground, is that as we have more users, we can take really expensive projects like building a ground station at Svalbard or building a ground station in Antarctica and share it among dozens of users rather than only having one buyer like NASA who can foot the bill. And so folks like NASA are then able to take advantage of that virtuous cycle by using the cheaper infrastructure to take their research dollars even farther to plan more space missions. So as we wrap up here in the last few minutes, there's quite a lot more work to be done. So this story has been incredibly rosy the last 10 years in terms of the growth we've seen in the space industry, in terms of the developments we've seen in the launch industry, as well as some of the frontier tech that's being done with exploration missions to Mars. We just had a fantastic flyby of Ganymede earlier this week as well. So there's quite a lot of exciting things happening in the space community. Where is there good work for good people to do? Oh my gosh, there's more work than we can possibly get done in a lifetime. These are the areas that really come as top of mind to me of the challenges that we need to solve to push the industry and push our community even farther. The first is economy of scale. We just talked about kind of that one-to-one relationship between a parabolic antenna to a satellite. Phased arrays or flat panel antennas could change that relationship. So right now, the technology is very real. It very much works. The problem is cost. So for most commercial missions, it is still more cost efficient to buy multiple parabolic antennas than to buy one flat panel. I'm really hoping that as we see more, more adoption of this technology in the coming 5 years, I hate to put bets on things, we'll say 2 to 5 years, that we'll be able to see a lower price for buying flat panel antennas so that the cost of use is more in line with the cost of a parabolic. And that's really just a question of cost, because from a tool perspective, there's not much of a feature set that is different for the LEO use case. The other challenge is around interoperability and ease of use. So folks like Yves and his team are working hard to help make it easier for people to use services. So rather than having to go out and buy ground station services, buy cloud services, buy networking, backhauling services, it can come in one package. That's going to save the space operator time to keep their engineering focused on things that haven't been done before, rather than tying up engineering time in procurement exercises. The second major challenge around optical, and perhaps our speaker from INERIC tomorrow will address this, is really about the industrialization of those systems. So we talked about things, and I hope that no one ever thinks of pigeons and now thinks of me. We talked about pigeons thinking on elements. pigeons also can have excrement that can fall in an optical telescope, and all of a sudden now your optical telescope doesn't work. So there are all sorts of silly things that can happen when you try to take a technology from a laboratory space to a 24/7 operations environment. That's really where the optical systems are right now, is trying to figure out how do we keep them online at high proficiency rates? How do they perform in tropical environments? How do they perform in very Arctic cold environments? Can we, as a service provider, be able to say to a customer, we can give you, at this point, even 98% proficiency, let alone the 5 nines that folks would, anticipate from a first-in-class system. There are kind of 3 different camps here of optical systems. So just a word of caution, as you think optical, the 3 camps have different challenges. I'm not an expert in optical systems, so I'll leave that for tomorrow's talk, but the space to Earth is probably the one that is most likely to happen first. Earth to space starts to have challenges with refraction as the laser is going to hit the atmosphere. So you need to have adaptive systems that can allow you to control for that refraction. And then free space optics, actually, I think we're going to see quite quickly as well as we look at the use of optical links between satellites. The third major challenge is spectrum management. So we started talking a little bit about how the licensing aspects are part of a site survey when you're choosing where to build. As we see more usage of spectrum, we're definitely going to need to have more tools up our sleeves in order to manage that spectrum more dynamically. So again, full transparency, I'm on this Commercial Small Satellite Spectrum Management Association. It's a whole mouthful, CSSMA. I'm a board member for that organization, and the goal of that organization is really to have an industry block to be able to work with the FCC as well as work with the ITU to be able to work together to figure out how can everyone achieve more by using this limited resource. We are also seeing a movement to higher frequency bands. So Ka band used to be the thing of the future back in 2006. It is now very widely adopted. NASA Near Earth Network has a Ka band component that KSAT is building for them. We're also seeing movements into higher bands like V band. And then the biggest challenge that I think is really the hard one to crack is the viability of the commercial market. So as we're talking about virtuous cycles, this economy of scale is huge in the space industry. So everything becomes both easier to do, higher proficiency, and cheaper at a higher volume. So it behooves the rising tides float all boats could not have been more true about the space industry, and that it behooves the industry to work together to figure out how to continue to build up this foundation of support. So there are lots of different business models, lots of different products that are being developed. You can kind of break them down into 3 major groups. So Earth observation missions, telecommunication missions, and government programs. Certainly the government programs will continue. I think we'll continue to see high investment from government agencies and government actors. Telecommunications there's a huge amount of investment going into the LEO constellations right now. I am very hopeful that we see folks be successful in this space. It is a huge capital investment that they're making. So the more that you're putting into building something, the more that you need to make on the back end to make sure that it can continue to be solvent. So I do think that this is an audacious program here, folks who are building the LEO constellations. And then Earth observation is probably the mission set that is most familiar to many folks who have been working in the industry for the last 50 years. Continue to see interesting innovations as folks try to figure out how do we make satellite data useful for people. So as people who are deeply in the weeds in the industry, it's of course inherently interesting to us that space programs exist. But for the average user, say my mother who lives in rural Iowa, why would she care about being able to access an image of, say, the field that is outside of her house, or of, say, the roads that her county is supporting? So how do we make sure that satellite data is actually helpful and useful to folks, or continues to be consumed? So in conclusion, I do think that there has been quite a lot of change in the last 60 years, which is a good thing. There continues to be a huge push and investment in our industry. So we'll continue to see more change, but absolutely some good work for good people to do. So do hope that folks are inspired or continue to be inspired to tackle some of these problems that we see that will help us move toward the future. So with that, Ankit, I think I have 2 minutes under time. I don't know if we have any remaining questions.
That's great. Thanks, Catherine, for the lovely talk. Fantastic. So any questions? We don't have any right now. in the chat. I think folks were happy to take the opportunity you provided them to ask them throughout. So I guess one question from there's another question here in the chat. What's the availability of KSAT commits to? What's the availability that KSAT commits to for ground station as a service? 95, 97, 99%. The question comes from Tony Colucci.
So Tony, such a good question. It really depends on the model. So for KSAT Lite, there's an SLA or a service level agreement that is associated with the KSAT Lite network. That's the 3.7 meter. It's very standardized. That's the network that is integrated into Azure Orbital. The hosting SLAs are very much on a case-by-case basis. So that is part of a conversation that happens between KSAT and OneWeb, for example, to say, what is the cost trade-off associated with that SLA? So that's really the trade space often, is the high level of proficiency can only be guaranteed by levels of redundancy. So do we need, we have a power generation, do we then have a generator on the site with us? Do we then have 2 weeks of fuel that we have stored so that we can make it through? So the higher the proficiency level, then there's cost associated with that. So typically that's a programmatic decision, particularly at the level that would be required for, say, SpaceBridge.
Perfect. Thanks, Catherine. Great talk. Really enjoyed it. So
great. Thank you all.
Thanks again. So sorry, folks, we have to move on to the next talk in the program. So please hold your questions for the panel discussion where Catherine is also participating. We can see if we can get time to pose some of your questions then. So we'll move away directly to Kirutika from Planet Labs. She's our next speaker. Welcome, Kirutika. Thanks for joining us. She's a director of engineering at Planet Labs. Her team builds Planet's Earth observation satellite avionics, high-speed compute and storage systems, and radios. Prior to that, Kirutika was a postdoc at the Kavli Institute for Particle Astrophysics and Cosmology. She built cryogenically cooled, there's a lot of long, big words here for me at this time of the night. She built cryogenically cooled ultra-low noise receivers to study the cosmic microwave background and star formation regions. Prior to that, she worked on NASA's Juno mission, as well as the Very Large Array in New Mexico. She has a PhD in electrical engineering from Georgia Tech, Atlanta. Please take it away, Kirutika. Thanks for joining us again.
Thank you, Ankit. Thank you for the kind introduction. I am going to try to project my screen and let me know if it comes through.
We don't see it yet. Yeah, now it's there. Great.
All right.
So we are still seeing the browser window framing though.
All right, let me change that. All right, hold on. How about now? How about
so
now?
We are seeing your desktop actually.
Okay, you're seeing my whole desktop.
Yeah. So the earlier view was better. I think if you're on Chrome, I think if you press Command Shift F, that probably, or Control Shift F, or Command Shift F, that probably.
Is this good? Is it sharing?
This is definitely workable. There's only the browser bar at the top. I don't think it's problematic. It depends entirely on your preference. We can see that you're.
Leave this.
Yeah, we can just see that you are a tab fanatic. That's the only thing. That's completely fine.
All right, I'll just leave it at this then.
Yeah, that's completely okay. The presentation is good. Thanks.
All right, thank you. Give me 1 second. I know you're recording this, so let me just try one more thing, and then if that doesn't work, I will stop it at that.
No worries.
All right.
So I think actually, if you go back to the view that you were in, if you just press Command Shift F, I think that will remove the browser decoration, but I'm not sure entirely.
All right. If this doesn't go away, I'll stop here and then
No,
maybe
it's
just
still the same,
share
but I
this.
think it's fine. Yeah.
All right. All right. So today, in this talk, I'm going to be covering Planet's communication network and how we've employed agile aerospace to be able to downlink a ton of imagery from our constellation. We've been, to just give a bit of background for why Planet's founded, I want to just talk about the challenges we are facing in this century as a civilization. We've been pretty lucky to live in a relatively calm period of prosperity over the last 70 years or so. We are 20 years into the 21st century, and we are facing some unique and complex challenges as a global community. The population is growing, and along with it, our need for food and energy and raw materials and living space. Global temperatures are warming, sea levels are rising, and weather patterns and disasters are seemingly becoming more extreme every year. This is from last year, from a wildfire in California that burned more than 4% of the entire state of California. This destroyed towns and led to extensive power cuts and polluted the air to a point where I live in San Francisco, we literally couldn't step outside the house for several days. And this is a mosaic of an image that's of the Amazon rainforest in Brazil. This is all illegal deforestation that's happening in the Amazon basin, land that's getting cleared to cultivate productive crops like coffee and oil and palm trees. And you can, we have access to imagery that shows that, first you can kind of see that the roads are coming in, and with time, tractors come in, they clear out the land, and this is happening on a daily basis. That Earth observation is enabling us to capture in very high cadence. In July last year, the last intact ice shelf in the Canadian Arctic collapsed, sending large ice islands out into the Arctic Ocean. And this was a picture that was captured in July, and 5 days later, the ice shelf broke off. And so we know that the environment is in crisis, and we're experiencing unprecedented rates of change that's already having significant impact on the lives of people all around the world and costing the economy trillions of dollars. With all the natural disasters that are happening, we are also living in a very dynamic and evolving geopolitical landscape as countries are facing new challenges, and populations growing, and people are getting restless. The bottom line is, we live in an incredibly complex and truly dynamic world, and the problems we face are planetary scale, and we won't be able to fix any of these problems if we can't see them and understand what is going on. And this was the mission that motivated the founders of my company to start my company with a vision to image the whole world every day, making change visible, accessible, and actionable. So we set about designing and launching satellites because we knew in order to see the world, first we need the satellites. And then we, when you started building the satellites, we realized we didn't have the software to make data accessible to those who need it. The software to control the satellites didn't exist to the scale we would like. The ground stations that were needed to meet our mission needs did not exist. So we kind of became a fully vertically integrated company that does everything from building and launching satellites to building and operating ground stations to automating to having an automated mission control system, as well as a data pipeline system that disseminates our data to the users. And today we are about 500 people working on this mission. We are in San Francisco, but we have a global workforce, including in Berlin, where we have a very big office. Planet operates 2 classes of satellites. About 150 satellites are always have always been operational for the last 5 years or so. Most of them are CubeSats. They're about this big, 5 kilograms in size, and we have about 130 of them. And they are the satellites that are imaging the planet on a daily basis. They have a 3 to 5 meter resolution, and they are imaging the planet daily. And then we have SkySats, which are much higher resolution. They have about half a meter resolution, so the resolution is about 10 times better on SkySats, which is great because if you combine the medium res and the high res, you're able to detect change that is happening on a with a lower resolution because these CubeSats are imaging the planet daily. And then whenever there is change, we can enhance or zoom in to a specific location by tasking the SkySats to go revisit that location at a higher resolution. So this gives us, in effect, a view of the planet, not just at 3 to 5 meters, but where change is happening. We also have a much better resolution and understanding of the change that's happening. Traditionally, Earth observation satellites have been rather big and expensive and take a long time to build and launch. These are a couple of pictures of NASA Landsat and the Digital Globe Worldview 4, and compare and contrast with Planet satellites that are much smaller and much lower cost to build. The only thing that Planet does is to build these smaller satellites, but much larger quantities of them, so that we could collect a large amount of data with these satellites. So our approach is to take a big, large, expensive mission and break it up into many small, cheaper satellites. And we operate all these satellites as if they are a single coordinated constellation. And there are a couple of important advantages to this disaggregated sensor network in space. First, if a rocket launch fails, or if a satellite, if you lose control of a satellite, then the missions are not entirely lost. You lose some capacity, but you have built-in resiliency into the network such that you can still meet your mission objectives. Second, it provides flexibility for us to upgrade. So we are launching 50, 60 CubeSats on a yearly basis. And what this allows us to do is to introduce change on an evolutionary basis, so we can upgrade our system on an ongoing basis and really have our satellites have the best-in-class technology in space. So having a disaggregated network of constellation allows us to put resiliency and provides us a direct path to upgrade the constellation capability. And in order to do this, we are a vertically integrated company. We do everything but launch, is what we say. So, so we build, we work with providers to launch, and we operate the satellites, and we only sell data to our end customers. So there is a concept called agile aerospace that has become quite familiar in the industry now, but Planet pioneered this philosophy of spacecraft development that that constantly relies on rapid iteration and prototyping, where the aim is to make small evolutionary changes to every subsystem at a time. And over time, the subsystem matures to an extent where it's very capable. What this means is that we need to frequently release new designs every 6 months, 3 to 6 months, and change the spacecraft design and accept the risk that's inherent to changing a design. This allowed us to change or upgrade our satellites. In the last 7 years, we've completed over 14 major iterations of the CubeSat, and the latest generation CubeSat is probably the in terms of its capability per kilogram, it's one of the most capable spacecraft that the industry has built. The other key aspect to agile aerospace, so one I said is the rapid upgrade path and continuous iteration. The second is to rely on, or stand on the shoulders of giants. We know the consumer electronics industry, the semiconductor industry, the automotive industry have been really pushing the technology envelope of what's possible. And Planet borrows heavily from those industries, batteries, the microcontrollers, the microprocessors, the solid-state storage devices, even our cameras come from these industries. And what we've done is apply careful commercial off-the-shelf technology in a careful basis by doing environmental screening, by selectively, providing redundancy where needed, and then test them in space, see what works, what doesn't. Over these many years, we built up a very good operational cadence of how to upgrade subsystems in space. And in addition, so you have this design, you've worked out this design, and now you need to make 50 of them and launch it in 6 months. How do you do that? That was only possible because we built lean manufacturing in-house with an emphasis on automated testing, in-house environmental screening and testing, and just-in-time production to build up to 40 satellites per week if needed. We also launch very often. We launch pretty much every 3-4 months. In the last 8 months, we've had 4 launches. We've launched over 436 satellites successfully. We've also faced a few failures along the way, but we've pretty much launched with everybody who can take satellites up in space. All right, once these satellites are launched in space, they go into the CubeSats, and I'm going to focus mostly on the CubeSats today. They go into a sun-synchronous orbit, and anytime they are over land, and if there is sunlight, they are nadir pointing, so directly pointing down and imaging, and continuously imaging. So these satellites sometimes would image for 20-30 minutes at a time, because you can get a global strip going from the Arctic all the way down to South Africa, and we would take that opportunity and image the whole strip. So you end up creating a new Google Earth, so to say, on a daily basis in space, and you need to bring all this data down. And that is one, a pretty tricky operation. And in order to do that, we had to build our own automated and very reliable communication network. We have a very small operations team. It's like, unlike NASA, where we have an operator, that's 3 operators per satellite taking turns. We have a team of 4 operators that are responsible for the operation of 130 CubeSats in space. And we couldn't buy a lot of the capabilities that we needed. So, we spun up a fully automated mission control system. So on the left side, you can see a couple of screenshots of one, the CubeSats are called doves, and you can see little white doves in the image. And then on the bottom, you can see some telemetry that we get continuously from all our satellites. On the right-hand side is one of our ground stations, very similar to what Catherine mentioned. And in fact, this site is very close to one of KSAT's sites as well. And we build and operate these ground stations ourselves for various reasons. This automated, reliable communication network is, in a sense, what made our mission possible. The big picture is when we want to talk to a satellite, the satellite talks to ground station, and depending on whether we are sending commands up or getting telemetry, those will go to the mission control. And if it's image data that's coming down, that goes to our data pipeline that ultimately gets disseminated to the users. The Planet ground station, we have about 46 different antennas at 16 geographically diverse sites, from Keflavik in Iceland to Awarua in New Zealand. We use these sites for both TTC, which stands for telemetry, tasking, and command. This is the low-speed system that always talks to the satellites at all time, whenever possible. And Catherine mentioned this wide beam antenna. We have a very similar configuration with an antenna that's extremely wide beam, so that no matter where 50, 60 degree orientation the satellite is, you could still talk to it. And then we also have high-speed ground stations that are used primarily for downlinking pictures. And the entire ground network is fully automated as well. And we have over 95% uptime in this automated network. And to date, we've downloaded, in the last 5 years, we've downloaded about 4 petabytes of data from our satellite constellation. So I'm going to shift gears a bit and then talk about the two antennas that enabled planet's Earth observation mission, but also in general for any Earth observation mission. These are the two critical pieces of radios that you would need in order to support the mission. One is a low-speed TTC, a radio. We call it the low-speed transceiver. It's it's open sourced now. We open sourced it a few years ago. And this particular radio is a pretty tiny radio. It's about this big, the size of a credit card, coupled with an antenna, which is you can see this little monopole, but it's an omnidirectional antenna coupled that's used for TTC, telemetry, tracking, and command, as well as ranging. We've flown this particular radio on over 400 satellites, so we had hundreds of cumulative hours of operation on orbit. It operates at UHF at about 3.6 kilobits per second. There are multiple ground configurations we have, and a couple of different ground stations are shown at the bottom right. And with this UHF network, we make thousands of daily contacts with our satellites. And if anybody is interested and want to learn about our OpenLST, you can, there's a URL that's provided at the bottom. You can go check it out. There are many university students that have launched their satellites with this open source radio that we released. To talk about the importance of this open source radio, I wanted to just provide a timeline for all the launches that we've made to date. I've said before that we've launched over 436 satellites. The latest build, we call it the SuperDove. That's the 14th iteration that I mentioned before. We've launched about 121 of them. And this gives a timeline. The last launch was about 6 months ago on SpaceX. About 48 satellites were launched. This plot, let's talk about the plot on the left, shows the time it takes to commission a satellite. Commissioning is from when you make first contact with the satellite. You have to do a bunch of steps, starting with detumbling the satellite, deploying the panels, and then some ADCS maneuvers to align the optical axis with the orientation, and there's things like moon imaging that they do in order to calibrate the optical the camera, for instance. So there's a lot of things that goes on. And initially, when we started out on the red, that's the Dove Classic, it used to take a long time. Each of these, the 3P, for instance, we launched about 88 satellites on that particular launch. But from when we made first contact to when the satellites were ready and taking pictures that could start selling, it used to be, on average, 40-50 days. And then we added a lot more frequent contacts, like with this LST network, as well as a completely automated commissioning phase, and that allowed us to continue, to improve the commissioning time. And you can see there's a jump up in commissioning time because this is brand new hardware, brand new software, and things had to completely change. But over time, the total number of days it takes to commission has shrunk. And with EP, there were only 4 satellites as opposed to 48 satellites. We were able to finish commissioning 48 satellites in about 13 days. And this is just about a dozen satellites in the SpaceX launch that we had in January. And you can see we could make first contact with all 48 satellites within 30 minutes from when they were deployed. And then from when the first satellite was contacted to when the last satellite started imaging, it took about 13 days. In a sense, having very frequent, reliable contact with automation is what allows us to quickly and efficiently commission satellites. Right. Once the satellite's commissioned, now what? Now we start collecting a ton of imagery, and all the imagery needs to flow through flow down from the satellite into the ground station into the cloud, and we use high-speed downlink network. On the radio, again, has been through this agile aerospace process where the downlink rate and the capability of the radio has been greatly enhanced over time. The operator X-band, it's a 6-channel radio, and you can see the 6 DVB-S2 channels, that's the modulation and coding scheme that we use on our satellite, is coupled to 2 separate polarization channels, and that allows us to have graceful degradation in case one of the channels fail. We still have the other channel, and we can downlink the data we collect from our satellite. At the bottom, you can see the X-band ground stations, which are about 5 meters in diameter, parabolic dishes. And the satellite system is very compact and extremely low power and can fit in a CubeSat. The radio that we built can downlink at about 1.8 gigabits peak data rate, and from one satellite, we are able to downlink about 500 gigabytes of images daily. So, so that's the radio that we built. But a radio cannot be all static because the link is very dynamic. The satellite, starts low on the horizon, it starts racing up, and if you traditionally, satellite designs were built such that you optimize the link for the worst case and add another 3 dB or 6 dB on top of that for those conditions. The point is, if you try to do that, then you cannot really push the envelope of what is possible. So what we did was to rely heavily on software and automation to try to optimize parameters on our satellite as well as the ground station, and the coding and modulation parameters are just a couple of examples, but we also change the power amplifier settings and other things in order to efficiently transmit as much data as possible at every slant range. So as the satellite climbs overhead, we start making contact at about 5-degree elevation, and the satellite climbs overhead. The signal to noise ratio, the plots are all received on the ground station. These are some of the metrics that we record. You can see that the signal to noise ratio starts climbing. And then the software automatically configures the modulation and coding parameter. We have an uplink, downlink, where every second the link is constantly checked. And if there's extra margin available, then the satellite automatically changes the power amplifier settings and the modulation and the coding settings as well. And then that directly translates to how much data we get down on the ground. These are, I said, the satellite has 6 channels, and these per channel data rate is stacked on top of each other. So the satellite starts at about a gigabit within a minute of starting the pass, and climbs to about 1.6 gigabits. And then as the satellite goes peaks and then goes down on the other side, the data rate also drops. This allows us to downlink something like 80 gigabytes of data per pass. If you had optimized for having static link that's always available, and you do not rely on software to continuously change the link parameters, then this throughput would be at about 20 gigabytes instead of 80 gigabytes that we are able to get on our satellite. So we also have a lot of metrics that we track on the ground, that we've telemetry, as well as how well these radios are doing and the communication networks doing, so we can constantly watch what is going on and upgrade or fix things when they break. This is a plot of how much data got downlinked from the doves. The green are the old doves. There are still a lot of the build 12, build 13 that are still in space, and there are not a few, but a lot of super doves. That's the build 14 that's in space, and we are getting about 175 terabytes of images weekly. If you go back all the way to 2 years ago, that we only had the build 12, build 13s. They were providing about 5 terabytes of data. And then we had to quickly figure out, we went from a 200 megabit radio to 1.8 gigabit radio, and that meant upgrading the entire ground station network. And because we were a vertically integrated company, it allowed us to be agile and on our feet. And anytime something changes on the satellite, we need to go to the ground stations, starting with, okay, we need to put in a dual polarization system, upgrade the front end, and then add the 6-channel demodulator, and lots of experimental configurations as we try to optimize link conditions all that had to happen over this period. So once the super doves, the yellow, started launching, we were experimenting and figuring out how best to operate them for about a year, and then we ended up launching more and more of them, and we have about 70 build 14s as the latest generation satellites, and about 50 previous generation satellites, that's the green, that are serving our customers. And today we are getting about 25 terabytes of data from these satellites. This plot just shows another, the agile aerospace philosophy again, and how that's helped this one particular system. This is the high-speed radio. This plot shows data rate. It's a log plot in kilobits per second of all CubeSats that have ever been launched up until 2019. I didn't update it after 2019. And the green is the $800 million, weighing a ton, WorldView 3 satellite. That's also an Earth observation satellite. And they operate at about 1.2 gigabits a second. It's the static radio that I spoke about. So everything's over spec on their satellite. And the doves, started out having a 3 kilobit radio, and with agile aerospace, upgrading one thing at a time, slowly over time, evolutionarily making jumps. We have a radio, the HSD2, that can downlink faster than the $1 billion plus satellite. So with careful application of commercial technology and taking some risk and upgrading your capability on a constant basis, you're able to slowly move the needle, and on specific subsystems have rival or sometimes exceed what much bigger and much more expensive and exquisite systems can allow you to achieve. All right, I want to summarize with this one slide that talks about just the communication needs for an Earth observation network. At least if you want to operate at the scale at which planet operates, there are 5 key components that make this mission of imaging the whole planet possible. And those are, and of course, having a very high reliability communication network. And then automation, getting people out of the loop and automating the contacts, having software drive, drive a lot of the contacts, for instance. Being agile, allowing upgrades, frequent access with our satellites. As I said, with LST, because we have frequent access, we can commission very fast. We can ensure within a few minutes that after deployment we can talk to the satellite. And then finally, because Earth observation missions are extremely data volume intensive, we needed to really push on the throughput or the downlink requirements on our system, and that's the other thing that we had to optimize. So I think I ended with plenty of time to
that's great. Thanks very much.
Questions.
That was a great talk, very insightful, and thanks for making time for questions. There are several questions already here in the chat. Kazim asks, are most of the downloaded pictures used or discarded? Would it be possible to use, for example, artificial intelligence, machine learning to decide which images should be downlinked?
Right.
Do you think that's useful?
So we download a lot of images, and a lot of times the imagery is not, I wouldn't say they are not useful early on when we deployed our satellites. We started imaging, and it turns out 70% of the world is covered by clouds, and 70% of land mass on any one given day is covered by clouds. That means 3/4 of the images, or close to images you get on your satellite are cloudy. Some people really want cloudy images. No one cares about where there are clouds, right? So you cannot just say, I'm going to throw out cloudy images, because that's bad business model too. So we do have some onboard, algorithms that run, that detect extremely blurry or extremely cloudy images. But on a CubeSat, there is very limited real estate for a powerful processor that can run these, machine learning algorithms. Hence, we focused on removing the bottleneck, which would have been the downlink, right? So because we were able to remove the data downlink bottleneck, we get all the images down today and then we do processing on the ground. And when we store imagery in the cloud, we know the data that we sell to customers, they are stored in a different location. And then, there are other data that we just archive because some customer would want to look at what happened 3 years ago over sub-Saharan Africa. And we want to be able to show, if there was a dust storm and that triggered a phytoplankton bloom, because there are researchers that are super interested in these kinds of questions.
Great question and answer. Thanks, Kirutika. A question from Sukirna. So forgive me, I'm not familiar with this acronym. So if you know, are the Planet Labs satellites are CCSDS compliant? So if you know the acronym, please also expand it. Otherwise, I can throw the question back to the questioner.
Yeah, so CCSDS is a waveform that is typically used for small satellites, CubeSats. That's a standard that was used. We were on CCSDS, but the waveform was very inefficient. I forget the acronym, so I would,
No, I think that's enough. So you've described what it does. That's okay.
Right, and then we found out that DVB-S2, it comes from the digital TV world, was much, they gave us modulation and coding parameters that were much more efficient. So we were able to pack a lot more, bits per hertz. So we moved to DVB-S2 primarily because, as I said, we want to have this adaptive ability to continuously change how much data we send, depending on the link availability, right? And CCSDS was the coding on the waveforms aren't as efficient.
All right, thank you. The last question is from Fadil Kurnia. Since many companies, Planet, SpaceX, now prefer to have small but many satellites, is there any coordination mechanism between companies or crash avoidance system? It would be great if all of those satellites can work together to give some resources to relay packets for. So this is, I think, unrelated. There's two parts to this. I can come to the second one later.
Okay. So we publish. So we are doing our own ranging, as I said, with our radios. And you have the JSpark network that tracks, where every asset is in space, any asset that's greater than 10 centimeter. We've realized that our ranging is a lot more accurate, for instance. So we publish all our satellites locations, every few hours on our website. And there is, there companies like AGI have software that can track where all the publicly available, information about satellites are. And then you would get a warning from NOAA if there's a collision that is potentially about to occur a couple of days in advance. And if there is, then we would maneuver our satellites to avoid it. So there is kind of a loose coordination that, it's only people who are willing to share their data that can publish at much better precision about the location. And then if companies aren't willing to do that, then you rely on the publicly available database, which could be kilometers off, for instance, from where the satellite is. But there are companies like LEOLabs that I'm super excited about, because they're building these big radars that can track objects down to like 2 centimeters. They are, I think people like them are going to change the game when it comes to space situational awareness, because if they can publish a catalog of all objects at 2 centimeter or greater, then that could have a lot of potential for when some of these mega constellations that are launching come up, and how do you maneuver around them. Thanks again,
Kirutika. So there's a follow-up to the first question, and I think we'll close after this one to get a 5-minute break. If a lot of the Earth is covered by clouds, why don't we use a sensor that sees through clouds? There are microwave sensors that might work.
Yeah, that's a good question. There are synthetic capture radar is a great example of a system that can capture very high resolution imagery, but can see through the clouds. But then the power and the size of synthetic capture radar is much larger. So if you want to do daily imaging, trying to have a synthetic and capture the whole planet on a daily basis, the synthetic capture radar is going to be several hundred kilograms cost you some, a couple of orders of magnitude greater than what a CubeSat can cost you, right? And on a CubeSat, on our system, for instance, we have multiple spectral bands. We have a spectral band that's optimized for looking at chlorophyll, and then another that's looking at the coastal blue that can really pick out the coastal regions very well, right? So we have it's an optical camera, but it also has other spectral bands that are optimized for agriculture, for oil spills, for instance. A synthetic capture radar, it does something different. So I would say in the future, synthetic capture radar, RF tracking with company like Hawkeye, hyperspectral, optical, they all have their place because they're providing different views of a region, and you construct a much better you construct much better intelligence with diverse sets of data, right?
Makes sense. Thanks, Kirutika. There's no questions, but we'll see if we can answer those in the panel if there's time.
All right.
Thanks, everyone. So we'll take a 5-minute break and return a quarter to the hour for the panel discussion. All right, then. Thanks again, Kirutika, and everyone else. Hi, everyone. Welcome back from the break. We'll soon be starting off with the panel. I'll start introducing our panelists. You've already heard talks from 3 of them, and 1 talk is scheduled for tomorrow. So I'll be rather brief, and just for the benefit of people who didn't see all the talks. So Eve Pitch is a principal program manager at Azure Space Microsoft. Catherine Monson is the former CEO of KSAT Inc. That's the largest ground station network. Kirutika Devraj is the Director of Engineering at Planet Labs, one of the leading companies in terms of satellite fleets for imaging. Gint Atkinson is the Vice President for Network Strategy and Digital Architectures at SES, which also operates its own low Earth orbit, medium Earth and satellite constellation. Gint is leading the transformation of SATCOM into 5G from the edge into the cloud. I'm giving some additional context for Gint because the others you've already seen talks from this afternoon. So with that, we'll get started. So I'll kick this off by first thanking you all for taking the time to do this. This has been a fantastic set of talks so far, and I'm looking forward to more tomorrow. So with that, one question I would like to raise is, how do you see the long-term evolution of the imaging space? So for example, with things like, so Catherine touched on several of these aspects, but more along the lines of the computer system side, like storage, right? So Kirutika mentioned there are customers that want to look back into the archives 3 years, 5 years back, do longitudinal studies. So how do you accommodate that kind of infrastructure, that kind of requests with limited budgets and infrastructure? What's your vision for how this might work out with increasing data over time and demands for long-term storage or archiving? I'll direct that to begin with at Kirutika, and of course, everyone should feel free. Otherwise, sorry, I'm putting someone on the spot, but
that's okay. I think, yeah, I've been seeing this for long enough that I need to, it's a challenge, and we hope people like Eves would help us with that ongoing challenge. But there was a time when Planet was established, when the biggest thing on our that would break the bank was a rocket failure, right? Like, because launches are super expensive, and then of course the hardware satellite cost was super expensive, but Planet found a way to reduce that, which was great. Then launch, we weren't launching, we weren't building rockets, so that was what could break our bank if there was a rocket failure. And then SpaceX came along and Rideshare came along, and launch isn't as big a problem anymore in terms of adding to the cost as it once used to be. And we are seeing now that like as we downlink more data, 25 terabytes of data daily, the cloud storage cost is turning out to be a huge fraction of what we spend. And with satellites, after a few years, they go out of commission. But once the data is on the ground, it's on the ground forever. So the data we have, we purchased a company called RapidEye a few years ago, and they have archival data going back to 2005, and we still host that data because some customers want to look at time series over the last 16 years of what has happened, right? And because the whole mission of Planet Labs is to create this time series that allows us to really see how the planet is changing on a global scale, it is important that we don't get rid of the data that we have. On the cloud side, we currently use Google Cloud as our partner, and what what they've allowed us to do is some of the data that is not as frequently requested gets stored in a bucket that is really affordable. It just takes a long time if a particular customer wants to request that location, because it's it's archived in a different place. But whereas the other more frequently accessed data, the data that's coming down, that is provided, that is provided much more readily to the customer. So that's number one. And at the end of the day, people love pictures; they love seeing pictures. But Catherine brought up the point that her mom doesn't really care about all these pictures that are coming down, and so does so does a lot of people, like people who are working for journalists that that want to know what is going on. They might be the ones that are interested in pictures, but for the most part, the commodities industry, the energy industry, and even the ag industry doesn't really care about what happened, in a pixel, in a picture, right? What they care about is information, right? Information and insight. So that's one of the things that Planet's been working on for the last few years, is to try to distill all the messages we have and deliver it to customers, as an insight. So if you have a huge farm, you're a farmer, and you've requested imagery of your hundreds of acres of farmland. Instead of us giving you the data, we instead tell you need to water a particular location every third day instead of every second day, and that would be enough. That's what they care about, right? So that's the next phase of what Planet is working on, is to provide value to the customers by providing the information that they need. And that's, Planet calls it that's our next mission, called Queryable Earth. And there's even a TED Talk from one of my co-founders about how we want to create a search engine for the planet, where you can query how many buildings are in a particular city in sub-Saharan Africa, and you can get that information. If and as it changes, you get the updates as well. So hopefully that answers the question of, it's pretty expensive, but at the end of the day, pictures are what drives the cost. But the value is really at the insight that we can distill from the imagery.
If you can complete that, I think I fully agree. Storage is one thing, but the monetization scheme behind is more important. And the fact that, I'm a bit biased being a cloud provider, but the fact that AI is accessible to more people, the tech, we give technology to more and more developers and more people who can use that to make sense out of the data. I think that is what's changing. A couple of years ago, AI was not so accessible. It was limited to a very specialized set of people, right? Now anybody can do AI, and that commoditization of the tech is helping to make use of the data.
Yeah, building up on Yves's point, SES's point of view was, yes, we wanted to get all of the cloud resources at cloud scale, at the best economies of scale and capability. But if you take a look at what we did together with Microsoft, you can see that we're getting an awful lot more from Azure. And of course, we're there for compute, storage, and networking, but an awful lot more. The big difference for us, and I think for a lot of Azure users, is we have what the enterprise needs, all the way from Dynamics for CRM, all the way down to the Azure for Operators, where we get a full BSS and telco stack from Amdocs, including ONAP, and then driving all the way down to our controllers, including our open space controller from Kratos, for example, and running our MNC inside of Azure, and then going a lot further. If you take a look at what we did together, the virtualization of modem platforms inside the Azure cloud. So when you look at the full stack that we're getting, BSS, OSS, orchestration systems, and the actual resource platform. So antennas plug into an RF matrix, going into an FPGA or GPU farm, and your baseband processing is happening. This architecture isn't new for Azure, because this is the architecture that they're using for the Cloud RAN. And this is where we're trying to move towards an Open RAN type of solution that we see in 5G and 3GPP. So when you look at everything that we're doing with Microsoft, it's a game changer. We're using what they do best, and we're trying to bring some of space to Azure Orbital. And it's a two-way partnership, but you can see we have economies of scale and economies of scope because of Azure and Microsoft's leadership in space as well.
Thanks for the inputs, Kent, Ivips, and Kirutika. So actually, that's a good transition point. The responses here to a question that's been on my mind for a bit now. And I think Catherine's presentation, there was this one picture of a satellite that sort of acts as a receiving station of some type for data. So what happens when, or is there a possibility that some of these operators like Starlink or SES or OneWeb will integrate some of these imaging tasks into their constellations? So I know that SpaceX, for example, files some FCC documents with synchronous orbits being part of their constellation. So are those going to be used for imaging? Are those going to be integrated, for example, with laser ISLs? SES works in both spaces, imaging and connectivity as well. So do you see a tighter integration between these, moving data down to the ground in more efficient ways? What do you think of this interplay between these two spaces?
So I think absolutely, the tighter integration is a must. You know, what's more provocative is how much capabilities we can potentially put up into the satellite. So as we get away from bent piped architectures and get increasingly digital, and we can do more processing up in the satellite, NTT announced that they want to do a data center up in the satellite. I think that might be a little bit challenging. The scaling problems may be challenging, but you know, I can definitely say putting some G-Node B capability up in a satellite is useful so that we can support terminal mobility. We can support mobility between beams, refocusing beams, controlling how the beams get configured, putting the radio intelligent controller up in the satellite as well, because I mean that software that's already there, but it's not standardized. So again, there's a lot of processing that we can get out of the 5G core and put the 5G core up in the sky. And as we get even more compute and more resources, I would guess that what I would do, I'm not saying what SES would do, if I could have a system on a chip that's a data center, that's not far away at all, and we can make it space grade, I would, instead of trying to reinvent the wheel, I would call up Yves and say, do I have bare metal in the sky that you want to use for Azure Edge Stack? I don't know. I would somehow think that maybe I could convince Yves that I've got a very valuable resource that he can bring what he has already, and that's, you know, that's going to be the 5G core, which Microsoft has, the edge capability, and an awful lot of other things. So I do think that announcement, a data center in the sky, I do think we should explore that and see what that does for what we can do in terms of processing. But I do think it's going to pull the cloud players to put capability, definitely edge capability up in the sky, definitely 5G core capability, and maybe even the RAN itself. I don't know, Yves, what do you think?
Well, we already have compute. I mean, if you look at the ISS station, we already have like some kind of edge compute capabilities. So it's not a new thing, it's coming. And I think there are two things I really believe is what Catherine said in her talk about multinodal type of communication. I think what's happening on Earth is going to space. So I can expect, I call it space pop. I'm not sure what should be the right word for that, but edge type of flavors running in space where we can interconnect networks. I think as from my window, that's something I see it coming. I see more players trying to act as a backbone in space, within orbit or across orbits. So this is coming. And then you're right. Now what next, like what you do with the payload, right? And I think it's back also to the standardization plays. Like today, you know, if you want to bring your own payload, you have to interact with the bus hardware. There's a lot of simulation, lots of things to happen. So the time to market is still long. We reduce the time to market by doing more simulation, less physical tests and whatnot. But at the end, the concept of hosted payload, you know, bring your own payload is coming. Now, what's the revenue model for that? Is there a market for that still, we can debate how much compute is required. So what Planet is doing, is great because it serves a very specific purpose. Now, if you want to expose that to any customers, maybe the rise of commercial stations like Axiom will, help bring new scenarios. But it's a matter of time. I agree with you again.
I have a slightly different take on this. The era of 2010 was about, I think what New Space did, not just Planet, but a lot of the companies, including SpaceX, did was to bring consumer technology, automotive technology, and try to, use that and really rely on Moore's law and bring Moore's law into aerospace and use that to quickly, cheaply, and efficiently launch and build out the constellation network. Now, what I hope to see happen in the era of 2020 is that constellations like SES would and SpaceX and Telesat and all these players who provide enough bandwidth in space with extremely low latency that I'm not saying edge compute is going to go away, but if you create a WAN, a wide area network in space with an interconnected sensor network, and you get real-time access to all the data, then why put a ton of compute in space? Get the data and then solve the problem on the ground. I'm not saying that that's what's going to happen in the near future. I think there's a lot of need for edge compute in space for people like Planet, because at the end of the day, if clouds, if only a small fraction of the revenues comes from the cloudy images, maybe we should get rid of them. So there is definitely need for edge compute, but I think if we could solve the latency problem, then running compute on the ground is so much cheaper than to try to put it in space. So there is a tricky balance that we have to.
So I have a really interesting story or description of how some of our customers behave, and I'm going to start off with the example. We're delivering a connectivity service to a remote enterprise, a big operation like a mine. So, they have a huge IT operation on the ground. They need machine learning. They have a lot of stuff going on the ground. Of course, in that scenario, the more edge you put on the ground, the less telemetry you have to send back to the cloud. So there's an edge architecture there. Now, what we found when we talk to our customers, and our telco partners on the ground are involved with this, because this remote enterprise, this remote business, they need to go to Azure. Most energy companies are going to Azure. So this is right away. We need to get to Azure. Now, there's a funny thing. With our mPower constellation, our beams are steerable, so we can pick you up at your remote and deliver wherever you want. We're in MEO, so there's an advantage versus LEO, for example. We have better reach, so we can pick you up in the middle of Africa and deliver you straight to the data center, the Azure data center in Dubai. And that is where we also have our gateway. Microsoft has a gateway virtualized, so makes total sense. 70 milliseconds one way. Now, but we have telco partners that are involved, and a lot of times the telco partner will say, yeah, we need to take the end customer straight to Azure, but we want you to pick the customer up in some African country in the middle of Africa, and then drop it off in country and get on our fiber network, and then go on a submarine network. And yeah, the fiber is not going to add too much latency, but all the routers in the way do. So the behavior here is kind of what it did was, when we start looking at latency sensitive applications, specifically mobile backhaul, there's a whole bunch of core network functions where 150, 200, even 300 milliseconds is more than enough, but we can do it in 70. And what we started to see, when we can land the customer straight at Azure and that's their destination, then we minimize the need for a lot of edge applications, especially if you're thinking of edge for mobile.
Yep.
Now, if the customer ends up landing at a gateway that is not at an Azure data center, and we need to go from the landing station, the gateway, and then backhaul terrestrially all the way to the Azure data center, as that distance gets greater, as that latency between the gateway and the Azure data center increases, there is a higher demand to put network functions at the teleport gateway. So there, and it's variable. You know, it depends on the route. It's topology sensitive and performance sensitive. So when you start thinking, you start doing these different connections, where are you landing, where are you terminating and handing off? As the distance gets longer for certain applications like mobile backhaul with a core network, you may want to be putting hosting EPC functions at the teleport gateway. And now that's something that we could put an Azure Edge stack there, and Microsoft can bring their entire 5G core solution to the table and host that there. So it does get complicated, not just technically, but there is buyer behavior. Those telco network engineers, they want to use their own assets. We like to say we're freeing the assets, make some more revenues, sell it to someone else. But it gets complicated with the buyer behavior as well.
That's very interesting. Thank you for that example.
Yeah, let me jump in because I have the advantage right now of being unaffiliated. So I think this kind of conversation that just happened is really illustrative of one of the dynamics.
I love where this is going with the unaffiliated. This is good.
Okay, good. I think one of the dynamics that I often see in the industry is we are an interesting industry because we are brought together because we use similar tools, but not because we solve the same problems. So the telecommunications part of the industry has one set of users. So the SES user group is very different than the user group of Planet. And so the Earth observation market, that product requires certain parameters. So latency in the Planet world right now, and Karthika, you can correct me, are you guys trying to get to X number of minute latency? What would the goal be?
Minutes. Yeah, many minutes, not milliseconds.
Yep, minutes. So that's, I mean, just even the unit there of minutes. Whereas telecommunications, you're talking about milliseconds. And then even within milliseconds, you know, the difference between LEO and GEO matters. Can you have a normal voice call, or are you just trying to pass data back to a user? Are you streaming video, which is, you know, has error correction, and so therefore it's a little bit more delay tolerant? Or, you know, again, are you having a two-way conversation of exchange that's, you know, going to trigger some type of action? So I guess I want to say to folks who are watching from the audience, one of the biggest challenges that I actually see in the industry from our professional workforce is that we often talk past each other because everyone sits in their little silo in the industry and they generalize that user group or that experience, when in fact we solve very different problems, and therefore we have very different parameters that are required to solve each of those problems. One, you know, problem set that Yves started to talk about when he was speaking about the value of security that hasn't been talked about very much yet today is the government market. So the government may put security as a feature set above everything else. So they may be willing to spend billions of dollars to build some type of infrastructure that maybe it can be replicated in the commercial industry cheaper or more quickly, but does it have the security features that they require? So that's kind of the question right now. Commercial industry is trying to answer to say, hey, US Air Force, let us build more things for you. We actually can keep up now with your security requirements. It doesn't have to be built internal to the government by, you know, the big primes like Lockheed Martin, Raytheon, General Atomic, L3Harris, just to be inclusive. So I think that's one of the conversations that is a market segment that I'm personally very excited about, is watching the US Air Force really take a very entrepreneurial approach in investing in a commercial industry to support that use case and those needs as a service, rather than simply building government assets that are going to be owned and maintained through, you know, government prime contracts. So again, kind of moral of the story here is we often talk across each other because we're looking at very different problem sets that are all served by maybe a similar infrastructure, a similar tool set, which is that space-based infrastructure.
So, you know, that's really interesting, especially on the tool point. But in our business, and talking from the SES perspective, remember we're content and connectivity business. We deliver content, over 8,000 channels. We're like the largest HD and UHD distributor, and we also do video processing, ingestion, post-production, ad ingestion, and then distribution. So it's a content business as well, and that content is also going into, you know, content caching with partners. But what I'm getting at is, are we a space business, or are we back into a service provider business that provides digital service? Now I hear Earth observation, and that's a digital service. You know, you're going to fly over after, like, my house in Japan got hit by a horrible typhoon, and the older neighborhoods got totally wrecked. There weren't any insurance adjusters driving around on the streets. They used Earth observation, and they processed those claims like in days. I mean, literally 10 days later, people were getting checks, and it was something like 90%. And that's an enterprise content business. So what I wonder, and I caution everyone, is if we stay a space business, we're a cottage industry, and we're doomed to vertical integration, and we better make it to Mars. If the assets that we produce go into the value chain that they do, they're wrapped up with the cloud scalers providing enterprises all sorts of digital services. They're going to consumers providing digital gaming, recording sports, digitizing sports on the fly in real time, so that when you do playback, it goes through a gaming engine, and now you can play back, you know, the content that you just watched in the game minutes later and do replays during the break. So, you know, are we a space business, or are we space tools to be in the business of digital content, connectivity, and reaching everywhere on Earth and beyond into deep space? So I think we get a little bit stuck on the days of tooling.
Right, Planet is a data company, and it just so happens that we launch our satellites because the data is provided by the satellites. We don't call ourselves an aerospace company by any means, because at the end of the day, you know, it's cool to build satellites. I'm on the satellite side, but what powers us is the value of the data that we can give to customers.
I can try to thread the needle that I'm hearing these different opinions on. I think it's mainly about where does the digital content originate. So different tools might apply in different ways if it originates on Earth and is distributed elsewhere via space-based connectivity, versus if it originates in space and is needed on the ground. I think that's sort of what I'm hearing with Gint arguing more explicitly that these are similar kinds of tools or progress is needed in the same kinds of ways, and others pushing back a little bit with it matters what the origins are, etc.
Oh, I think we're actually saying the same thing. I think we're in violent agreement. And I think maybe the take home is focus on your customer. Your product is defined by being helpful to a customer. So Krithika may have a different customer than Gint. At KSAT, my customer was folks like Krithika and folks like Gint. So how then, as a company that provides services to space companies, how do we figure out what their challenges were to be able to improve our own service? So I guess my take home here is that let's not get too caught up as an industry on the fact that space is cool, because it's only cool if it can help someone and someone wants to buy it.
Yeah, and I think, you know, there's the flip side points, the supply side, demand side perspective. The supply side of the money is strangely coming from an awful lot of extremely wealthy individuals that have other businesses that need the value that the space assets produce. And those individuals have very close ties or directly wrapped up with cloud scale businesses, cloud services. So, you know, we have SoftBank. We look at what's Rakuten going to do in space. It's going to be interesting that they'll probably be bringing a lot of ground technology eventually to bring 5G to space-based access networks. But the big thing is there's a lot of money coming from cloud providers, and that means that, you know, the supply and demand balance is really important there. We could be pushed in the wrong way, or we could be pushed in the right way. I think SES's experience with what we're doing with Azure, I believe, is right on for the whole space industry as well.
So I think we are already pretty close to time. So I think I'll take the liberty of asking one last question to the panel, which is, in the imaging space, the number of ground stations you needed thus far was not that large. It's good to have many more, of course, but you don't need thousands typically, right? So it's a pretty small number. But now with the massive scale broadband constellations like OneWeb, which doesn't, at least initially, plan to deploy inter-satellite links, they'll end up needing many more ground stations. So especially for the ground station folks, Eve and Catherine, and perhaps Kirutika as well, what are your comments on how you see this developing? So how are we going to move from a few tens of ground stations, big sites worldwide, to perhaps thousands? So what's the change? How's that going to happen?
Well, it takes a lot of work. So both OneWeb and SpaceX Starlink have fantastic teams of folks who are working on this challenge. Starlink, and all of this is public if you check the FCC filings. I'm not saying anything I shouldn't. Their architecture requires many, many more ground stations than have been the case for previous architectures. It goes back to trade space. So having more gateways is a cost driver, but it also provides redundancy. Iridium is an interesting counter. You know, it's on the other side of the spectrum on the trade space, in that they have so many inter-satellite links that they operate, you know, a handful, like we're talking 4 or 5 various locations around the world that support the entire network. That is, you know, it truly is a network with the ISLs. So, you know, I do think it's just a trade-off on architecture. It's a hard problem to build many ground stations, because you do start to have to, as we talked about, it's difficult to do site surveys. There are a lot of factors that can disqualify a site. So you're really trying to find the needle in the haystack of a place that has all the things that you need. And it's a cost driver, because once you build hardware in a location, you have to support it for the length of that constellation, or until you don't need it anymore. So I'll be curious, because I do think that the inter-satellite links are going to change the dynamics of that trade space. SpaceX is a hugely impressive company because of how adaptive they are. So I would say to folks, just because they're building something today doesn't mean that they think that that's the 5-year architecture or the 10-year architecture. So truly, I think SpaceX is really resilient in their ability to say, how do we get to market quickly? How do we get this product and service out to folks? And let's adapt as we go.
Yeah. Just adding to what Catherine was saying, I think SpaceX has launched 1,600 satellites, and only a handful of them have inter-satellite links. But their network architecture really relies on the OSLs, and the latest claim is that they are working on not just 1 gigabit or 10 gigabit, but hundreds of gigabits, maybe close to terabit capacity of the inter-satellite link. And the slowest link, if you have 4 satellites you're interconnecting with your optical network, and then you have a ground station link, the bottleneck will be whichever is the slowest, right? So if you can solve the OISL problem on orbit, and if you can build a fat pipe to the ground, then you can drastically reduce the number of ground stations you need. But it's a regulatory challenge, right? Then you're like a country like, say, Russia, would they be comfortable routing all the customer data through a US-based company that's that's routing data in space? Maybe not. And that's why OneWeb decided to not go with optical inter-satellite links, although they are changing their narrative lately. they decided to primarily go with bent pipe structure, and so did, like SES. It's great to just be a bent pipe because you're in MEO and you're so far away that you can land, with extremely low latency at a particular ground site and still, have packets coming in and out of the same regulatory region. So it's a much correct me if I'm wrong, but regulatory wise,
we're not bend pipe. We have a switch in the sky. So this is kind of an important detail. That is the fundamental capability that lets us put the TTNC on a gateway, but when instead of picking up, going to the satellite, going down to the gateway, going back up to the satellite, and then out to your endpoint, we're able to go from point A to point Z. So we can call that an in-country gateway if you want, but with a MEO scale constellation, we don't have the problem that you have in a LEO where you really need more and more ground stations, and your coverage and capacity, it's a real challenge when you need to have a gateway. And I suspect that the mega LEO constellations are going to be pushed into going down a path where the gateway, you go towards a gateway-free architecture. Add one more thing in, 5G NTN, and look at all of your tower companies. You're going to have the edge compute there. You have the radio resources you need there. All of a sudden, every single tower location that a tower company is operating at with significant edge and RF resources, all of a sudden that's one of your ground stations. So you'll be able to pick up and deliver capability and capacity on a much more point-to-point fine-grained manner. So, what we're finding with what we sometimes call a gateway-free architecture, that opens up a lot of possibilities. It complicates the control plane. But doing things like possibly using a user terminal as a relay to a ground network or some other network. So, but this becomes a fantastically complex control plane with all of these nodes shifting in a interwoven fabric of different orbital planes, and your path in the sky and the ground is changing, especially if you're bouncing around from ground to sky. So I think we are going to find, especially at large-scale LEO, we're going to find a lot of challenges on the control plane that need to be solved. But where you don't have as many satellites, like the benefits of MEO, the simplicity offered there, and maybe taking advantage how you could simplify the topology by inter-satellite links between different orbits, between LEO, between MEO, maybe even GEO when it suits, and bypassing the terrestrial network. But now what you need to do is a multi-network optimization and include the whole end-to-end path, the terrestrial network, the multiple constellation satellite networks between different providers. And all of this really leads you in towards the only place where you can manage all of this complexity after you get the right algorithms, after you solve Doppler shift and all the other stuff we bring to the radio problem. It's probably going to be around a bunch of enhancements to the 5G control plane.
Those are great insights, Ken. Thanks everyone. So I'll leave the last word to Eve because the cloud company got a little left out here in the end. So with any comment from Eve, we'll close.
No, it's great. I think a couple of things. If I look at the US, there's many locations, many counties in the US where I simply cannot have a ground station. We have a data center in Phoenix that sits across 2 counties. On one county, I couldn't have the antenna. On the other one, I could because of FCC regulatory and 5G overlap. So that's one challenge. Second challenge is the amount of data we have to process. So we need big pipes. So that's important. Again, in the US, you have these big fiber pipes, like we have these ILA, where the fiber is going out of the ground, where we can just drop, antennas close by, and we are just close to tons of capacity. Now, what will change is with intersatellite communication, I expect some gateways to be bigger. So we have different flavors of gateways, and maybe new bands. Like we talk about KA, but I'm hearing more about V-band, more complex, but there's a need to maybe skip also the regulatory aspect and maybe use new bands, to address that. Optical ground stations, I don't know, the tech is not new, but it's coming, more and more into the market. So I expect also the ground station to evolve over time and to address more capacity, and the biggest challenge is always regulatory work behind. That's what's slowing us down. Yeah.
Great. Thanks, everyone, for your contributions. And it has been a pleasure talking to all of you. Thanks for all the insights. I learned a lot here. I hope our viewers did as well. Thanks again for all the great talks, and looking forward to Gint's talk tomorrow as well. That'll be all, folks. Thanks, everyone, for watching along, and see you all tomorrow. We'll have a great set of talks again. See you tomorrow then.
Thank you.
Bye.
Thanks.